Hello everybody, my name is Hernan Llano and welcome to the first week of Studio FX workflows. I'm going to start by introducing myself very quickly. I have been doing CG for over 10 years now, and I started as a CG generalist doing pretty much everything, but I very quickly realized that the mix between art and science that goes into creating effects was really what I enjoyed the most. So I eventually decided that I was going to focus mostly on doing effects, more or less around 7 years ago. I started working mostly on advertising on small companies, but at some point I felt that I wanted to push myself and work doing effects on bigger projects, and I did realize that the only way to do that was by learning Houdini. So I put a lot of my free time into learning that tool, and eventually I started working at Dineg in London. After that, I also had the chance of working at Framestore for many years, where I did work as an effects artist, effects lead, and also as a supervisor. And I'm currently working at ILM as a senior effects TD. So now that you know a little bit about me, I'm gonna talk a little bit about the workshop too. So what this workshop is about. We're going to be creating a lot of HDAs. And during the process, you're gonna see me making mistakes, you're gonna see me fixing those mistakes, you're gonna see me creating interfaces for those OTLs, and in general just creating the whole setup. I'm gonna explain in detail every single step I'm doing. I'm not just gonna go ahead and do something and not tell you why I'm doing that. I'm gonna take my time to describe every single step. I'm gonna teach you how to approach complex problems step by step, how to break down a big problem into smaller problems, or at least how I do it, how I think about what the inputs and the outputs of my setup needs to be, and then based on that I build the tools. I'm gonna show you how to build your setups in a way that it's easier for other artists to pick up, because remember, you are part of a team. The setups that you do are not just for you, are also for other people. So we need to keep in mind that there is nothing more annoying than picking someone else's scene when that scene is a mess. So I think one of the most important things you can do is keep your scene clean from the beginning. Don't wait until the end. And finally, most of this workshop is gonna focus on the setup building. We're going to be doing a lot of destruction, but the destruction is not the focus. My focus is on the actual workflow, not the effect itself. And at the end, you should end up with a nice set of tools that are a very good starting point for your setups. You can, of course, go ahead and improve them. I'm gonna try to keep them as simple as possible, so then it's easier for you to add on top of that. So just to show you very quickly what tools are we going to be doing, I'm just gonna bring Houdini. And what you can see here are some of the tools that we are going to be creating. Not all of them are here because by the time I'm recording this video, I haven't finished yet with all the videos, so I'm gonna be creating more of them. But we're going to be doing some tree destruction. We're going to also be preparing the geometry. So we're going to create some utility tools that are going to allow you to prep the geometry for destruction. We are going to be using constraints a lot. And of course, we are going to be using bullet. We are going to be creating a bullet wrapper. And if I dive inside, or actually before I dive inside, this is the interface. You can see it's fairly simple. You have an input that reads geometry, one input that reads constraints, and two other inputs that read both geometry and constraints for the feedback, which I'm gonna explain in detail when it comes to creating these tools. If I dive inside, you can see it's very simple, which means that it's very easy to modify and keep adding on top. And this is what you will see at the end on the wrapper. We're going to be using some wrangles, constraints, and we're going to be modifying the geometry and the constraints during the simulation by using solvers. And because we have one shot where the spaceship or a spaceship is colliding with the ground, we are also going to be doing some tools to create ground interaction that should be useful for other type of effects, not only for the spaceship. So what this workshop is not. This workshop is definitely not an introduction to Houdini. I'm not going to explain what the difference between subs and dubs is. I'm not going to explain the interface. I'm going to make the assumption that you are already familiar with Houdini. This is not going to be an introduction on Bullet, Pyro, or Vex, although we are going to be using them a lot, so I also expect some familiarity with them. And finally, we are not going to be doing any rendering. This is not going to be a rendering workshop, because otherwise it will be too long. And I think that's a topic for a different workshop. Again, as I said before, the focus is the workflow and the setup. So what specific topics of Houdini are we covering or using? We are going to be using a lot of Vex. Of course, we're going to be doing some destructions with Bullet. As I said before, we're going to be creating some HDAs. Because we need to do transformations, we are also going to be using some matrix transformations in Vex. At the beginning, it's going to be very simple. And then when it comes to the trees, it's going to get a little bit more complicated, but it's not going to be too bad. We're also going to be doing some wedging in order to speed up the process, because I'm going to be working in a single machine at home, which means that I don't have access to a render farm. And there are some things that I just don't have enough RAM in my computer to do. So what I have to do is split that process in different chunks that I can actually run in my computer. And I'm going to show you how to do that. I'm going to talk a lot about scene structure. And because I make the assumption that you are familiar with Houdini, I'm not going to explain how to dive inside nodes, how to go outside of those nodes. I'm just going to do it. And I expect you to know what I'm doing. We are going to be using some Python, but just in very rare occasions. It's going to be very little Python, mostly at the beginning to create some shelf tools. And inside the HDA module of the bullet wrapper, we're going to also be using some Python. But if you are not familiar with Python or have never used, don't worry. I'm going to explain each line and what it's doing. And again, Python is not going to be used that much. So what are the prerequisites of this workshop? As I had mentioned before, I expect some familiarity with Vex. I'm not going to explain what variables are, how to create attributes in there. We're going to be creating 1 or 2 functions. So I kind of expect you to know what a function is, although you don't really need to know it. We can just implement it. You need to be familiar with the different contexts, like subs, dobs, vobs, and so on. I'm not going to explain what they are and when to use them. I'm just going to go ahead and use them. You shouldn't be afraid of using some linear algebra. And by that I mean just basic operations that anyway you will have to use every single day as an FXTD. And those are mostly dot products, cross products, vector addition, subtraction, and finally some matrix multiplications. You should also understand how VOPs works, although I'm gonna be using mostly Vex, that's what I like using the most. But because we're going to be using some VOPs, I expect you to at least be familiar with it. And I think one of the most important things to know is subs. So I expect some familiarity with subs. You should know what attributes are, how to create attributes, and how to use them. And finally, and most important than everything else, I expect you to have the will to research, try things on your own, try to come up with your own solutions, and don't give up when you get stuck with something. I'm not gonna give you a recipe of steps of press these 3 or 4 buttons and that's gonna give you the best result possible. This is not a workshop about that. I'm not gonna go ahead and iterate over and over and over until we get the best result possible. I expect you to do that. I'm gonna show you the way and then it's up to you to follow that way. Now, when it comes to homeworks, we're not gonna have that many because this is a very hands-on workshop. I expect you to follow every single week because basically, you can't do the next week without doing the previous one. You need the tools and the setup that we built in the previous weeks. So basically, the homework is just keeping up and doing all the tools, doing all the setups. So with that said, I think in general, this workshop is geared towards intermediate people who's got some experience with Houdini. This is not meant to be an introduction to Houdini, keep that in mind. But if you already have some experience with it, I think you can learn a lot from this workshop. I don't believe that what we are doing is extremely complex. I think if you put the time, it's actually easy to follow. So I'm pretty sure you can learn a lot from this, especially if you want to get into the technical aspect of Houdini and building tools for other artists. So that's pretty much everything you can expect from this workshop. In the next video, what I'm gonna do is I'm gonna talk a little bit more about what we're going to be doing in terms of the effects, and I'm gonna explain a little bit more the steps that we're going to be following. And I'm also going to be giving you some theory on how to create OTLs, what OTLs are, why there's kind of a distinction between HTAs and OTLs, what are OTL definitions, operators, and so on. So I'll see you in the next videos. That's all I have to say for now. Bye. Okay, so once you download the folders, what you're gonna find is a folder called Destruction Effects. This is the project itself, and then inside you're gonna see another set of folders. The first one being the asset folder, and that's where you are going to find everything that we're gonna be using during the project. If you go back up, you will see another folder called Examples, where I'm gonna be placing some files that I think are going to be useful for you. Inside Framework, I'm gonna be saving the files where we are going to be creating some of the OTLs. And then there are 2 other folders, RB Ground Collapse and RB Spaceship. Inside RB Ground Collapse, we have everything that is related to the shot where we are going to be doing the big ground destruction. And you can see that there are some folders already in there. This is the set of folders that Houdini creates by default when you create a new project. And if you go back up, you will see RB Spaceship, and this is the folder where we are going to be working on the spaceship destruction shot. On both of those folders, you're going to find a Houdini file that has the word start. This is the file that we're going to use to begin our setups. And what I'm going to do now is I'm just going to open the spaceship start file, and I'm going to show you what you are going to find inside. Once you open the file, what you're going to see, it's an almost empty file, but you're going to have one archive that's going to try to load the camera, one node that it's going to load the environment, and another node that is going to load the spaceship. If I go inside the environment, you will see 3 different alembics. And you will also see that those alembics are failing. And the reason is that they can't find the alembic geometry that they are pointing to. And that's happening because there's an environment variable that I'm using called project. And the first time you open the scene, that environment variable won't be set for you. So I'm going to show you how to set it up very quickly. If you go to the edit and then aliases and variables, and then you go to the variables tab, what you need to do is write the name of the variable. So I'm going to write project, I'm going to hit enter, and then in here I need to write the path to the project. And that's going to be, in my case, on my hard drive D, Rebelway, and then destruction effects. Just make sure that it's pointing to the project and not to the shot. Okay, so once you have that path in there, hit enter. And what's going to happen is that those nodes are going to be able to load the geometry. And you can see the environment here. This is what we are going to be using to work. And the other nodes should be able to also load the geometry. The other variable that I want to set is the job variable. So I'm going to go ahead to edit, aliases and variables. And inside job, I just want to point to the same folder as the heap file. So I'm going to select the heap variable. I'm going to Control C the path, then go back to the job variable and paste the same path in there and hit enter. And once you are done with this, the only thing you need to do is save, and that's going to save those variables inside the file. If I look from the camera that should be loaded now, you can see that we have an animated camera. And you can see that we also have a frame range already established, which goes from 1001 to 1090. But the animation of the spaceship, it's definitely longer than that. So if you want, you can extend the frame range and do a longer shot. I'm just going to keep it like that, just to be able to iterate quickly. So this is all you're going to find inside those folders. In the next video, I'm going to actually start talking a little bit more about what we are going to do and how we are going to do it. So I'll see you there. Bye. Welcome back. So the first thing I always do before starting to set something up is look at what I did receive from both modeling and animation. And in this case, it's the environment and the spaceship. So let's have a look at the environment first. You can see that we have 3 different files, and each one of them have different resolutions. Usually for effects, depending on what you need, but usually the low resolution is what you're going to be visualizing most of the time, unless it is very different to the high res. But in this case, I'm pretty sure, because of the scale of this environment, the low res is the one that we're going to be using most of the time. As you can imagine, if I go to the mid res, we should be seeing more detail, but also it's going to be it's going to have a higher resolution compared to the low res. And then the high res should be pretty heavy, so I won't be looking at this one most of the time. So we are going to only worry about this one once we start doing rendering. The other thing I always look at is the attributes that we received. So the first thing is that we know that this is an alembic, which means that this is going to be a packed alembic. And very often you're going to have an attribute called path. And this path is very important. It's an attribute that you always want to keep. You don't want to delete it or modify it at all, because this attribute, it's basically describing the hierarchy of the geometry in Maya or whatever other piece of software they use at your company. So you don't want to change this, because there are other departments also relying on using the path attribute. In this case, I'm pretty sure that this path attribute is pretty much useless. Mostly because this geometry was generated in Houdini, and also because we know there's not other departments using this. So I'm not going to worry that much about the path when it comes to the environment. But before moving into the spaceship, I want to unpack this geometry and see what we have inside the geometry. So if I middle click here, you can see that there are some point attributes that were probably created by the hide field tools, like the bedrock, debris, height, and so on. And there's an attribute name, but we are missing the path attribute, which I mentioned before. Something that we don't really need in this case, but usually when I do unpack geometry, I make sure that I always transfer the path. So we always have that path attribute in the geometry. So now we have polygons and they still have the path. Now that we know what we have in the environment, let's go back and have a look at the spaceship. So if you have a look here, the spaceship have basically the same attributes. We also have a packed alembic. And if you remember correctly, we also have a camera. So I'm going to have a look at the camera and I'm going to look at the animation. And just as we did with the environment, we have to look at the attributes that we have on the spaceship, because most of those attributes are going to be useful for us later. As well as the environment, we have the path attribute, but let's have a look at what we have once we unpack the geometry. And you can see that we have a name attribute, which seems to be empty. I'm going to transfer the path attribute, and I'm going to look at the path attribute and see what we have. And this seems much useful than what we have in the environment, because we can see that the hierarchy here, it makes sense, not like the other geometry, which is not useful at all. We also have those detail attributes that are not useful for us. We have UVs, we have a normal in the vertex, and that's pretty much it. So the attribute that we are going to be using the most is the path attribute. The name seems to be empty, so I'm not going to worry about the name. So now we know what we have. We have a spaceship and we have an environment. We know that the spaceship is animated, so that means that we have enough information to start planning up what we are going to do and how we are going to solve the problem. So let's go back up. Before placing any node or setting something up, what I like to do always is write down my ideas, kind of break down what basically needs to be done in the shot. So I'm gonna bring something that I started doing before, and I know we are gonna be doing some RBDs. Those RBDs are going to be used for the spaceship because we are gonna be doing some destruction. The metal needs to be deformed. There are some particularities to doing RBDs on animated geometry that make it a little bit more complicated than just destroying a building, for example. And we are going to look at that at some point. I'm also going to do some ground destruction on the shot and trees destruction. And you might be wondering, how do I know what I need to do? Well, the thing is, I did this shot before. I don't have any animatic or anything like that. Usually you will get an animatic or some sort of brief of what needs to be done in the shot. From what we can see here, we're gonna need some RBDs for the ship when it hits the ground. We're gonna need some RBDs for the metal bending, although it's not very clear here, but there's some metal bending happening on the spaceship, some deformation. It's just that most of it is covered by smoke and all the other effects. We're gonna be doing some grains, you can see here as particles, and also we're gonna be doing some smoke. So in general, all those effects can be grouped into kind of categories, which I was doing here. So grains, we're going to be using some vellum grains and also some pop grains. For the particles, we're going to be, or actually for the leaves of the trees that basically came up from the trees when they are hit by the spaceship, we're going to use particles. We are also going to use particles for some secondary debris. We are going to use the pyrosolver for the smoke that's coming from the ground, for the smoke that it's coming from the spaceship, because in theory that spaceship it's hitting the ground because it was hit by something else. I'm not sure what, but it kind of justifies the fact that the spaceship is falling into the ground, and possibly we're gonna create some fire. So usually what I do before starting working on a shot is I do this. Why? Because then I can break this up into what I need to do for each one of those aspects, and that's what you can see here. So for the animated spaceship, I know that I'm going to be doing some metal bending that involves some RBD systems and also a very heavy constraint setup, because those constraints are the ones that are going to keep everything together. I also know that the spaceship is animated and that animation was approved by someone else. Like when you are working as part of a team, your work usually comes after someone's work, right? In this case it will be the animator, or it will be the modeler. In this case it's the animator, that person who animated the spaceship. So we need to basically keep that animation, or at least the feel of it, and we need to make sure that whatever we do, it's gonna use that animation. So that's why I wrote here it's a guided simulation. It needs to be guided. For the ground destruction, I want to create a setup that is not only going to work for this shot, but it could potentially be used in other shots, and also that's fairly easy to use, so we can iterate quickly. So what I want to do first is create a tool that will create some sort of deformation on the ground, and it's also going to create some attributes after that deformation. Why the deformation? Because I would like to use that deformation to guide any other setup, like for example a destruction setup or a particle setup, whatever it is. I want that deformation to be the main guide, and I have a flipbook here that hopefully it's gonna work or give you an idea of what I mean by the deformation. So you can see that the spaceship is leaving a trail, and that trail, it's going to guide, or it's going to have a very heavy influence on the other simulations. And it's very easy to tweak this kind of system because it's not very heavy. So we know more or less how far from the spaceship we are going to have that kind of bulging or influence from the spaceship. And you can see here that we are leaving some gap between the spaceship and the ground. I'm going to explain all those things later, but basically what we are doing here, it's leaving some space for the RBD dynamics. But this is what I mean by the ground deformation. And this deformation should create some attributes that we are going to use later down the line to create all these particles. And it's that deformation that's going to also trigger all the RBDs that we can see here. So once the spaceship hits the ground, you can see that there are some RBDs happening, and those RBDs are going to be colliding against that ground deformation. I'm going to show you very quickly the final kind of file. It might be a bit different than this at the end, because this is the file that I prepared originally. But so you know what we're going to be doing. We are doing some environment preparation of the geometry. We're going to be doing some preparation of the spaceship geometry. And usually when you're working at a project, a very long part of your time is going to be invested into doing this preparation. And it's probably the most boring part, because I mean, usually what you want to do is, you know, do the destruction, whatever you want to do. But quite honestly, most of the time is going to be spent into the preparation of the geometry, going back and forth between you and the animator, because probably the animation is not working for effects, probably the modeling is not done for effects, so you're going to find yourself going back between modeling and effects. So I think it's a good idea to expect that and to get used to that. After the preparation of the geometry happen, we are going to do actually the actual setup for the dynamics and for, in general, for the spaceship, for the ground, and at the very end we're going to prep some nodes for rendering that later can be used on Arnold or in Mantra or whatever render engine you guys used at the company. Here I have some examples of what we are going to be doing. On the left you have the tools that come from side effects, and on the right you have some of the tools that we are going to be building. So for example, there's an RBD bullet solver, which is the sub wrapper of bullet made by side effects. We are going to create our own, and we are going to also create one for constraints and one to configure the constraints. I'm putting one next to the other just to explain you why we are doing this. And you might be thinking, why don't we just use this? That's a good question, and the reason is because I want to show you how to create tools. So we're not going to be building something as complex as the ones that come from with Houdini. We are going to be creating simpler versions of those tools. But I think it's a very good practice to create your own tools, even if it's just to practice, because that's going to give you a better knowledge of the low-level nodes that come with Houdini. I think that's very important, because in recent years, what side effects has been doing is creating a lot of wrappers, which are great tools. I mean, don't get me wrong, they are very good, and I encourage to use them. But if you learn Houdini by just using these tools, you're going to be missing a lot of what makes Houdini so good. And I just don't want to go ahead and use them. I want to teach you what's going under the hood. And for that, I think it's very good to create a very simple version of this tool. So if you dive inside this one, actually, let me open it. If you dive inside here, you can see there's a bunch of nodes. Our own is not going to be that complex. If you dive inside, it's very simple. And then we're going to go into DOPS, and this is what we are going to be building. We're going to create node by node, and I'm going to explain you what is happening under the hood. Again, it's not going to be as complex unrobust as this, but it's gonna be a very good example on how to build your own tools, and hopefully it's gonna help me teach you Houdini in a better way. We're gonna do the same for the constraints, and we are gonna be doing the same for the configuration of the constraints, plenty of other setups. So that being said, I think that's good enough for this video. I'm gonna teach you a little bit more of theory in the next one, just before we actually start doing the setups. But I think it's very important, especially as a mid to senior artist, to know that kind of theory, because that's kind of the backbone of what you do day to day. So I'll see you in the next one. During this workshop, we are going to be creating a lot of OTLs. So I think it's a very good idea to give you some guidelines and also a refresher on how to create them and just an explanation on what they are. If you go to the examples folder, you will find an OTL start Houdini file that I'm gonna use to explain you the whole process. Let's go inside the OTLs node, and inside there you will see a very simple example where we have a sphere. We are adding peaks up and then some points on top of the geometry. And then on the second network box, we are setting a p-scale attribute on the points, and then we are copying some spheres onto those points. So my plan is to separate each one of these processes into an OTL, and I'm gonna use that process to explain you what an OTL is, how to create an OTL, and how to modify the parameters and so on. So the first thing you wanna do when you're gonna create an OTL is select the nodes that you wanna place inside the OTL and press Shift-C on the keyboard. Once you do that, you're gonna get a subnetwork, and if you dive inside the subnetwork, you have the nodes that you basically selected before. I'm gonna do the same with the copy to points, and now we have two subnetworks. The next thing you want to do is select a proper name for the OTL. So in this case, what we are doing is creating some points. So what I'm gonna do, it's called the OTL create points. And then the second OTL is gonna do something completely different. It's gonna actually copy some spheres into those points. So I'm gonna call this one points to spheres. Once you have those subnetworks created, what you need to do is start promoting some parameters so the user can control the nodes from outside. And in order to do that, you're gonna go into the edit parameter interface. And I'm gonna talk a little bit more about the edit parameter interface later. For now, I'm just gonna promote those parameters. The first thing I do is I select all the inputs, which are these parameters that you can see on the subnetwork, and I'm gonna hide them by ticking on the invisible toggle, and then I press apply. And now you can see those parameters are hidden. The next thing I do is I go inside and then I start thinking on what parameters I want to expose to the user. You don't want to expose every single thing because probably the user don't really need to have access to all the parameters. You only want to expose to the user the parameters that you think are going to be useful later. And in this case, I think the distance is going to be useful. And from the scatter, you can also promote the total amount of points and the relax iterations. You can expose other parameters, but in this example, I'm just going to expose those. So I'm going to create one folder for each one of these nodes. And you can do that by going to the create parameters, and then you select whatever you need to create and drag it into the existing parameters. I'm going to create two folders, and then I'm going to give them a name. So select the first folder, and then go into the name parameter, and I'm going to call this one peak distance. And on the label, I'm going to use the same thing and press apply. What you can see here is that I'm using lowercase for the name and uppercase for the label, and I'm also using spaces on the label. The name is what is going to be recognized by Houdini, and it's what you're going to be using if you are going to be doing some scripting. And the label is what's going to be seen by the user on the parameters. What I usually do is I set both of them to be almost exactly the same, so then later it's easier to use them if you are writing any sort of shelf tool or script. If you press apply and then you go out, you will see that now you have two folders. And those folders are currently what you would call a tab. And you can see that the folder type of both of them is set to tab. If I were to change them to simple, and this is what we are going to be using most of the time, you will see that they disappear. And by default, when they are empty, they just don't show up in the interface. So what we need to do is start dragging some parameters in there. So let's dive back inside the create points, select the peak sub, and then let's drag and drop the distance parameter and press apply. You can see that by dragging the parameter in there, you automatically have a name and a label, and it's going to use exactly the same name and label that you had on the node. And the parameter, it's gonna be immediately linked to the node above, which is basically the subnetwork. So let's go back up. You can see that now we have a folder and we have the parameter in there. If you want to change the default value, you can go to the channels and swap the value to something else. So say, for example, if you want the distance of the peak to be 0, so it doesn't do any change by default, you just change this value to 0 and press apply, and you can see that it changes to 0 immediately. If you move the value, what you will see is that the number now it's bold and it's brighter, which means that the parameter was changed. If I set it to default, which is 0, you can see that now the name of the folder, it's again not bold, and the number, it's also looking normal. So that's something good to keep in mind, and that way you know that the parameters are not the default values, for example, or that they are not set to default. Okay, so now we have the distance, and that's the only thing I want to promote from the peak. Now what I want to do is promote the values from the scatter. So I'm gonna select the second folder, I'm gonna call it scatter, and then in this case I want to make sure that the user knows that we are talking about points. So I'm gonna call it scatter points, and I'm gonna do the same on the label and press apply. Now what I want to promote to the user is the total count. So I'm gonna drag that parameter in there, press apply. You can see that now it's linked. And I also want to promote the relax iterations. So I'm gonna drag and drop and press apply. You can see that on the left of the parameter we had a toggle. So I'm gonna also drag that toggle and I'm gonna place it above the relax iterations and press apply. If I go above, you will see that the toggle now it's on top of the parameter, and I want it to be on the left. So what you need to do is select the toggle and then activate the horizontally join to next parameter and press apply, and you will see that now it's fixed. But if you go inside the subnetwork, you will see that you had the label for the parameter, but you didn't have the label for the toggle. So I'm gonna select the toggle and I'm gonna deactivate the label and press apply. So let's go back up, and you can see that now it looks the same. So for now, these are all the parameters that I want to promote to the user. I'm just gonna click accept, and I'm gonna save my scene. So I'm gonna go ahead and save this file. Now the next thing I want to do is create the parameters on the another OTL that I'm gonna be creating, which is the points to spheres. So let's go ahead and do the same. Edit parameter interface. Let's hide the inputs, press apply, and let's look inside. In this case, the sphere has a radius of 1, an uniform scale of 1. I'm gonna leave it like that, and I'm gonna set the radius to the default value. So the only parameter that I want to promote to the user is the p-scale. So I'm gonna create a folder, and I'm gonna call it p-scale. And I'll set the folder type to simple, press apply, and drag and drop the p-scale parameter in there. And I wanted to show you this because if you set the name of the folder to p-scale, you will see that the name of the p-scale parameter that we dragged into the folder, even though originally it was called p-scale, now it has a different name. And the reason is that you cannot have repeated names into the parameters. You definitely can have repeated labels, but not repeated names. So what I'm gonna do is I'm gonna select the folder and I'm gonna update the name. And I'm gonna use sphere p-scale rather than p-scale. Then select the p-scale parameter and I'm gonna remove the number 2 from there and press apply. So now you can see that p-scale, it's pointing to the parameter p-scale on the subnetwork, and click accept. So now if I go above, we are ready to create the OTLs. So what I'm gonna do is I'm gonna duplicate the subnetworks just to have them as reference. And this is something I always do. I basically replicate the subnetwork and then I create the OTL. That way I can go back if there's a problem or something happens with the pipeline. And I'm also gonna duplicate them because I want to show you what's the difference between a subnetwork and an OTL and how different it is to create parameters for one or the other. So I'm gonna select the create points and I'm gonna create an OTL out from it. So in order to do that, you can right click on the subnetwork and then there's gonna be an option called digital asset. In other versions of Houdini, you will see another option called create digital asset, but it seems like it's not present anymore. And if you hit the create new, you will see an interface that pops up. And there's quite a lot of different useful parameters in there, but we are not going to be using them all. So I'm gonna show you which ones we are going to be using. We are going to be using the type name. We are going to also be using the menu entry, the label, the author. We are not going to be using any branch, and we are not going to be adding any prefix type category. So I want to explain you very quickly what the type name is and what the label is. So I'm not going to create the OTL for now. I'm just going to click cancel. And then I'm going to go back up, and then let's go into the name and label. So in here I have 3 different scatters. The first one is called my scatter, the other one is called my other scatter, and one more scatter. All of them are exactly the same OTL, but they have different names. So what I want to show you is that there's something called a name and something called a label. What you are seeing here is the label, but that's not the name of the node. If you want to see the name of the node, one way to do it is by click the node, and then you will see the operator name in there. So you can see that it's called scatter2. You can also see the name here, and you can see different definitions. I'm going to talk about definitions in one moment. So you can see that this one it's called my scatter, but the operator name it's actually scatter2. This one's label it's my other scatter, and the operator name is also scatter2. So you can see all of them share the same operator name, but they have different labels. So I'm going to go back up, and then I'm going to go back into the OTLs folder, and let's go ahead again and go to the create new, and then the type name it's going to be basically the operator name, and what you see here it's going to be the label. What I do is that I always keep them the same. You will see me on the workshop making some mistakes, and then I will have to fix them, and it's because I didn't keep those values the same. So what I will advise you is just keep them the same, and I will deactivate the branch just because I'm not working in a company right now. I'm just creating OTLs for myself, and you will be creating OTLs for yourself in this case. The versioning, because we are creating the OTL for the first time, it's going to be of course version 1. The prefix type category, it's basically adding to the name of the OTL the context where you are creating the OTL. So in this case, we are creating the OTL in subs, so you can see it's adding the sub as a prefix. The menu entry, it's also very important. When you're going to create a node by hitting tab on the keyboard or by right-clicking, you will see that there's a lot of different labels here. Whatever you write here, it's what you are going to see as an option. So if you want to create all your OTLs inside a tab that's called My OTLs, all you need to do is write here My OTLs. So for this example, that's what I'm going to do. But later we are going to be using RB, which stands for Rebelway. So let's do My OTLs for now, and let's deactivate the prefix type category. I don't want to have the word sub in there. The other thing that I want you to see is the save to group of parameters. The library path, it's where the OTL is going to be saved. So by default, that's going to be saved on the Houdini user pref dir, and that's basically on your documents folder if you are on Windows. If you want to see what the user pref dir is, all you need to do is go to @export and then write echo and the name of the variable. And then you hit enter. You can see that in my case, that's on my user folder, the name of my computer, which is called Rabbit for some weird reason I don't even remember. And then inside documents, we have the current version of Houdini, which in my case, it's Houdini 19.5. And then what's going to happen is that on top of this path, it's going to add another folder called OTLs, and your OTLs are going to be saved there. If you want to create another or use another folder for that, you have different options here. But during this workshop, we are going to be using the Houdini user pref dir. Something to keep in mind is that by default, the author is going to be using the name of your machine. And remember, my machine is called Rabbit. In your case, it's going to be something completely different. If you don't want to be changing this all the time, what you can do is just hit cancel. And then if you right click on the subnetwork and then you go to digital asset preferences, you will see that you have a lot of different options here that you can use to basically modify how the new digital asset behaves. So what I'm going to do is I'm going to add a new author here, which I'm going to call RB, and I'm going to activate RB, and that's going to stand for Rebelway. I don't want to add any branch namespace. For the asset label, I want the label to be automatically set to the same name of the asset. For the menu entry, I'm going to use something like RB or my OTLs, as I said before. And I don't want to prefix the type category into the name of the operator. So I'm going to use this set of options as they are right now, and then I'm going to click apply. After you click apply, what is going to happen is that once you go to the digital asset, create new, you will see that branch is deactivated. The menu entry is set by default to my OTLs. The author is automatically set to whatever you wrote here. And I forgot to deactivate the prefix type category, but what should have happened is that this was deactivated. And you can see that the label of the node is automatically set to the uppercase version of the type name. So in this way, you can basically automate how this is going to behave, or at least make it easier for you. And that's going to basically help you to make less mistakes. This is something that I realized when I was halfway through the recording of this workshop. So you will see me having some problems with this because I didn't know that I could change the preferences. This is kind of new. So I'm just gonna deactivate or close that interface, and then I'm gonna click create. What's gonna happen is that the type properties interface of the OTL is gonna pop up, but also if you go into your documents folder, you will see that the OTL was created and the author name is added as a prefix, and then the name of the OTL, the version, and then the extension, which in my case, it's HDALC because I'm using Houdini Indie. I'm gonna talk a lot about this in a moment, but for now I'm just gonna close it. I'm gonna select the other OTL or the other subnetwork, and I'm gonna do the same exact thing. So I'm gonna click create new. And you can see that because we set the preferences, now everything is correctly set for you. So I'm gonna click create. And again, we have the type properties interface. So I'm gonna close it. So the first thing I want to mention about OTLs is that what you are seeing in the scene, it's an instance of that OTL. The actual OTL, it's a file on disk, which you can see here. So you can imagine OTLs are kind of like a recipe that tells Houdini how to create those nodes. So when another user is using an instance of your OTL, or it's creating an instance of your OTL, they are basically creating a node based on the recipe that you created. And those OTLs are automatically added to the list of nodes that Houdini can find. And if you want to know where Houdini is looking for those nodes, there's one variable that Houdini uses by default, which is called the Houdini path. And if you want to have a look at that variable, all you need to do is go to the text port and write echo Houdini path. And this is the list of folders that Houdini looks by default in order to find where OTLs are, where scripts are, and basically where to find everything. If you want to know more about those variables, what you could do is go into the Windows tab and then open a shell. And then inside the shell, you need to write hconfig. And then if you hit enter, it's going to show you the variables that we are currently using. And you can see that we are using Windows. We can see where Houdini is being installed. You can see that home points to your documents. You can also see the Houdini user pref there that we saw before. And if you want to see what other variables we have access to, all you need to do is write hconfig ap. And you're going to get a really big list of variables and what they do, how to use them. So have a look at that if you want. If you want to add additional folders, you want Houdini to find OTLs in those folders, what you need to do is set an environment variable called Houdini OTL scan path. And this is an additional folder where Houdini is going to look for your OTLs. But again, by default, we are going to be creating all the OTLs in the user pref dir, so I'm not going to set this variable. Okay, so now what I want to show you is that if you right click on the OTL and then you go to show in Asset Manager, you're going to open another window, which is the Asset Manager. Another way to open this window is by going into Assets and then opening Asset Manager. But when you do it from the OTL, it's going to immediately show you the OTL and the HDA. And I'm going to talk about what the difference is and what they are for in one moment. For now, I'm just going to close the Asset Manager. And what I want to show you now is that there's a difference between subnetworks and OTLs. One is that the subnetwork, it's basically a node that only exists in your scene. So if you want to share this node with someone else, you will have to either send them a path to your file or find a way to share the CPIO file that gets created when you hit Ctrl+C on your keyboard. So say, for example, I hit Ctrl+C by selecting the create points subnetwork. Once you do that, a file called subcopy.cpio is created on the Houdini temp folder. And if you want to see where that temp folder is, all you need to do is echo temp, and you can see that the temp folder is here. It's going to be different on your computer. And if I go to that folder, what you will see is that a file called subcopy.cpio is created. And you can see that the context where it was created, it's also in the name. So if you give this file to someone else and they place that file here on their temp folder on their own computer, and then they hit Ctrl+V, they're going to basically copy that node in their scene. Usually companies have that option on their pipeline already, so you don't have to worry about that. But with OTLs, it's different because if other artists have access to where those OTLs are saved, all they need to do is just call that OTL. So for example, we already create the create points OTL. So all they need to do is basically create another instance of that OTL. And that makes OTLs extremely good for working with other artists and as part of a team. Another difference is that the parameters in an OTL are actually parameters that are embedded into the definition of the OTL. while parameters on the subnetwork are called spark parameters. When you're going to modify the parameters of a subnetwork, what you do is you select the core here and then you go to edit parameter interface. But when you're going to edit the parameters on an OTL, what you do is that you select the OTL and then you right click on it and then you go to type properties. And then you go to the parameters tab, and you can see they are extremely similar, but their name it's different. You can see that on the OTL you are opening the edit operator type properties, while on the subnetwork you are just editing the parameter interface. On the OTL you are actually editing the properties on the operator type, while on the subnetwork you are just adding spark parameters. What I want to show you is that if you select the OTL and then you go to the core and do edit parameter interface, you can see that those parameters now are grayed out. And I want to show you the difference. If you go to the type properties, you will see that those parameters are actually looking brighter. And what this is telling you is that these parameters are actually part of the operator type. If I were to add parameters to this OTL by using the same technique that you use to add parameters to the subnetwork, what you're gonna do is you're gonna add spare parameters. So let me do that now. I'm gonna select the OTL. I'm gonna edit parameter interface, and then I'm gonna add a new parameter, which is going to be a string. I'm gonna call it my string, and then I'm gonna click apply and accept. You can see that the node now has a parameter called my string, but if I create another instance of the OTL, you can see that that parameter is lost. It no longer exists because that parameter is only present on the node or on the instance of the node inside your scene. If you actually want to add parameters to the OTL, what you will need to do is you will hit right click and then type properties. So what I'm gonna do is I'm gonna remove that parameter from there, and in order to do that I need to do edit parameter interface and then remove it from there. Or what I'm gonna do is match the current definition first, and then I'm gonna remove that parameter by selecting the parameter and then hitting delete on the keyboard, and then I'm gonna click accept, and now we remove that spare parameter. What you will want to do if you actually want to add parameters to the operator type, it's right click on the node and then go to type properties, and then in here you will actually add the parameter. So I'm gonna add a string, I'm gonna call it my string, and I'm gonna click apply. When you hit apply, you can see that there's a pop-up telling you that you need to unlock and save the node. Let's say that it's okay, and then I'm gonna click accept. And the OTL it's open. When you are doing changes to the OTL needs to be open. That's why it basically did that for you. But if I select this node, you can see that now, even though we didn't do any change on it, you will see that my string it's actually added. I'm gonna talk a little bit about why this is kind of risky and why it is also very good. So just bear with me. I'm gonna match the current definition, and what that's gonna do, it's gonna basically look for the definition in disk, and then it's gonna match this instance to that definition. So say for example, if I open the OTL by selecting it and doing allow editing of contents, and then I'll add another node here, like say for example a null, and then I right click and match current definition. What's gonna happen is that because that null is not saved on the definition in disk, if you dive inside, that null is lost. And I've seen many people adding a lot of things inside an OTL and then matching the current definition, and basically everything they did is lost. And I think this is a good moment to talk about open OTLs and closed OTLs. You can see that OTLs have a little icon next to them, this little lock, and you can see that some of them are gray, and this one, for example, have a red lock. What that means is that this OTL is currently open and this OTL is currently closed. Usually what you want to do is work with locked OTLs all the time, especially if you are not doing any modification on them or if you are using someone else's OTL. So say for example, one of your friends made this OTL and you are just using it, you are not modifying it. And then at some point during the scene, you open the OTL because you just wanted to look inside or you wanted to change a parameter or something. And you forget that you opened that OTL and you leave it like that. And at some point your friend do a modification to the OTL. He or she updates something. And what's going to happen is that your OTL or your instance of that OTL is no longer in sync with the OTL that your friend did. And there's no way for the OTL to know that there's a new version of the definition in disk. And now you basically have an outdated OTL. So in general, it's good practice to keep your OTLs closed. I'm going to talk a little bit more about good practices in a moment. But for now, it is just good to know that it's a good practice to keep your OTLs closed. So I'm going to explain you now what an OTL is. What you're going to see is that some people call them OTLs and some other people call them HDAs. In my head, they are exactly the same thing. And I'm going to call them interchangeably during this workshop. Most of the time, I'm just going to call them OTLs. An OTL is basically a file in disk that stores multiple definitions of different digital assets. And I know that the explanation doesn't make much sense. So what I'm going to do is I'm going to show you first that when you create an OTL, a definition is saved on disk. In the past, those definitions were called OTLs, and that's why most of the people calls them OTLs. And as you can see, the folder is still called OTL. And each one of those OTLs can contain different definitions. So that's what OTLs means. It means operator type library, and it was called library because it used to contain multiple definitions. Nowadays, that's not longer used that much. It's not actually considered a good practice to have multiple HDAs inside a single OTL. So these days what we do is that we store one single definition per OTL, and that's why you just call them the same, OTL or HDA. And I'm going to show you how to create an OTL that contains multiple definitions in a moment. But I just want to show you in this image what I mean by that. So say, for example, you are working on a framework that does RBD. And say that you decided that you're going to use a single OTL that's going to contain all the definitions. So you can see that in this case, I have one single OTL that I called RBD framework. And RBD framework contain different HDAs. So I have one HDA that is the RBD solver, another HDA that contains the constraints, and another one that does the transformation. But all those definitions are stored in one single OTL. While if you were using multiple definitions, what you will do is you create one single OTL, which will be the RBD solver, and that OTL contains the one single definition, which in this case I call the same. And if at some point you needed to create an RBD constraints OTL, all you need to do is just create another OTL that's going to store a definition that it's called the same. And in general, I think using multiple definitions is the best way to go because you might have different artists working on different OTLs at some point in time. So say, for example, you have user 1 working on the solver, but you have another user working on the constraints, and you might have another user working on the transform. So you have 3 different people working on 3 tools at the same time. And because those tools are stored in different OTLs, each user can basically modify those OTLs without worrying about the other tools because they are basically different OTLs. While if, for example, you use the single definition approach, you can't have different users working on different definitions because all of them are stored in one single file. So if you have 2 artists working on different definitions, what's going to happen is that if at some point one of the users want to push the changes that they did, what's going to happen is that the other user is going to basically lost whatever they did because you cannot have the work of both users merged together. So you have to decide which one you're going to keep. So in general, we are going to use multiple definitions. So let's go back to Houdini, and I'm going to show you what the OTL and the definition is for create points. So right click on the node and click on show in asset manager. And you can see that you have the operator type, which is the HDLC, and you have a definition inside. And you can see that below it, we have also the points to spheres, which is another OTL that also contains its own definition. So I'm going to create another OTL that's going to contain both definitions inside, rather than one definition per OTL. And I'm going to show you the difference. So let's close the asset manager, and I'm going to duplicate these subnetworks. And what I'm going to do is I'm going to rename them to single def. And this is just to keep track of them. What I'm going to do is select the first one, and I'm going to right click, and then I'll click digital asset, create new. I'm going to keep everything the same, but I'm going to modify the library file name. So what I'm going to do is click on automatic, and I'm going to choose custom. And what you see here, it's the name of the OTL, where the definition is going to be stored. I'm going to call that OTL test OTL. So I'm going to remove part of the string, and I'm going to replace it with test underscore OTL. I'm going to copy that name, and then I'm going to click create and accept. So now we have an OTL, and you can see that it is pointing to this path in disk where the OTL is stored, and you can see that we have only one single definition. You can also see that we have one OTL additional here, which is the test OTL. And now I want to create another OTL, or actually I want to create another definition inside that OTL. And what I'm going to do is select the other subnetwork and right click, digital asset, create new. I'm going to keep everything the same, but I'm going to change the library file name to custom. And I'm just going to paste the same OTL name. So you can see we are pointing to the same definition or the same OTL that we were using before for the previous OTL. And I'm going to click create. And you can see that Houdini is immediately telling you that the library file already exists, and that in general, saving a new library is a better practice. And this is what I was telling you before. Right now, I don't care about that, so I'm gonna click confirm. So now you can see that the library is the same as the one that we used for the previous OTL, so I'm gonna click accept. So both of them are pointing to the same OTL, but the definition is different. You can see that in this case it's RB points to spheres, and in this case it's RB create points. And if I go to the folder, you can see that no OTL was created. We still have one single OTL. And if I right click on the node and then I go to the asset manager, you can see that now we have one OTL that has two definitions. So I just wanted to explain you what's the difference between OTL and HDA and why I'm going to use them interchangeably. I also wanted to show you that you can keep multiple definitions inside one OTL. And finally, I also wanted to show you that we are going to use the approach where you basically have one definition per OTL. I'm going to close the asset manager, and then I'm going to just match these definitions. We're going to be doing a lot of OTLs during this workshop, so I'm going to explain you a lot more about how to create parameters. But what I wanted to show you in this case is that, say for example, you have an OTL and you want to modify that OTL so it contains another OTL inside. And then you want to expose the parameters from the low-level OTL to a top-level OTL. So what I'm going to do is I'm going to take the OTL that we already created, which is the points to sphere, and I'm going to place it inside. So you have the chance to see how that works. So I'm going to create a points to sphere inside the create points OTL, and I'm going to place it there. And say we also want to have control on the top level OTL so the user don't have to dive inside and modify the p-scale. What you will do is you will select the OTL, the create points, and then I'm going to right click on it and do type properties. And then what you can do is you will create a folder, and you can call that folder however you want. I'm going to call it the same name as the OTL, which in this case it's points to spheres, and it's going to be a simple folder. And then one option will be to take the parameter of the low level OTL and drag it inside the folder that you created and press apply. And now you can see that the p-scale is connected to the top level OTL, and now you can control that parameter from here. I'm going to click accept, and now you can see that you have control from outside. That's definitely one option, but I don't usually do that, because if you want to do a change on the points to spheres OTL, that change is not going to be reflected on the create points. So what I do all the time, I use the import settings inside the folder. So I'm just going to remove that p-scale parameter, and I'm going to unlink the parameter from above. Let's revert to defaults, and I'm going to click apply. So now we no longer have that parameter in there, and the points to sphere is no longer connected to the top level OTL. And what I do instead is I select the folder where I want to bring the parameters from the low level OTL, and then I toggle on the import settings. And then you have three different parameters. The ones that I'm going to be using are the source and the token. So for the source, you just need to give it the path to the node inside, and you do that by using something called opt syntax. So because we are inside the create points, all you need to do is write up column and then the name of the node that you want to call. So we know that that node is point to spheres. I'm going to remove that, and I'm just going to copy the name or the label of the node in here and press apply. And then for the token, I need to point to the folder that I want to bring to the top level OTL. And that folder is the sphere p-scale. But because I don't know the actual name of the folder, I only know the label. What I need to do is go to, or what I always do is I go to the from nodes tab. I look for the node where I am, which currently it's the create points node, and then I open that node. And then you can see everything that is inside there. And you can see that there's another node called points to spheres, which is this one. I'm gonna open that node. And when you open the node, what you will see are the nodes that are inside there, basically all the nodes inside that OTL. But you also see the folders contained inside the definition of the OTL. And you can see that the folder sphere p-scale, it's there. So if you middle click in that folder, you will see the proper name. And it's sphere p-scale without spaces and all lowercase. So what I'm gonna do is write the name of that folder and then press apply. And what's going to happen is that if you go to a top level OTL, you will see that nothing changed. And what you need to do now is click this little cork icon and then hit the refresh imports option. And you can see that you have an interface telling you that there's a processed block and that we added the sphere p-scale, and then from there we added the p-scale parameter. Hit OK and press apply. And now you can see that we have the p-scale parameters in there. Click accept and then save node type. So this basically does the same thing as just dragging the parameter from the low level OTL. But now if I open the points to spheres and then I add something to the sphere p-scale folder by going to the type properties, and then adding something else, like in this case, I'm going to add a string. And I'm just going to call it test string and hit apply and accept. All I need to do is select the create points OTL, right click, type properties, and then refresh the imports again. And you can see that now the string is added. And all I need to do is click accept. And now we have the test string in there. So in this case, it's not a big deal because we only added one single parameter, but say you are working on this OTL and you add a lot of parameters, using the import settings is going to save you a lot of time. So I will advise you to do that. And then one last thing I want to mention about creating those OTLs is that in this case, I created the parameters before I created the OTLs, but you could do the opposite. You could just create an OTL out from an empty subnetwork. And then rather than adding the parameters from the parameter interface, what you will do is create the OTL. The OTL wouldn't have any parameter. And then all you need to do is just hit type properties and start adding your parameters in there. So now that we know what an OTL is, what an HDA is, what definitions are, I want to talk a little bit about good practices when it comes to working with OTLs and especially working within a team. When you are working as an FXCD, it is very likely that you are going to be part of a team, and there's some things that I want you to keep in mind, which I call OTL good practices. The first one, and I think the most important one at the beginning, is that you should ask before creating any OTL. And the reason is that because you are part of a team, especially if you are working on a big company, it is very likely that someone already did what you are trying to do. So using someone else's tool not only is going to help you saving a lot of time, but because that tool was used already by other people, it means that it was already tested and it is very likely to work well. So you rather use that tool rather than creating a new one. If you think that you can improve that tool, then go ahead and create a new one, but always ask before so they know that you are working on it. The second thing that I want you to keep in mind, and I think it's the most important thing once you are creating OTLs, is that because it is very likely that other people it's using your OTL, especially if it's a useful OTL and people like it, it is very risky to save versions on that OTL because you might break other people's scenes. And I'm going to show you what I mean by that. So I have a simple scene where I'm trying to emulate what will happen if you have different users using the same tool. So here you have the OTL, and the OTL is connected to a pig head. And I have the word creator because let's pretend that this is you and you are basically working on your machine with your OTL. And user 1 happens to be doing the same. They are using your OTL. User 2 is doing the same, but they have your OTL open. And user 3 is doing the same. They also have the OTL open, but he is not only opening the OTL, he's also modifying your OTL. So let's pretend for one moment that you say, okay, I like the OTL, but you know what? I'm just going to add something else. I'm going to add something new. I'm going to allow editing of contents. I'm going to dive inside. And I think that adding a point jitter to my geometry is just going to make it look much better. So I'm going to add a point jitter, and that's it. I'm happy with the change. I'm going to save the OTL. So you can see that this is the current state of my OTL. This is the output, which means that the output is not what it used to be before. And say user 1 is working with your OTL, but he sent his job to the farm, and he's not aware that you are modifying the OTL. Actually, nobody else is aware because you didn't notify them. And then you go ahead and say, okay, I'm good to go. I'm going to save the node type, and I'm going to match the current definition. So see what happens. User 1 has something completely different to what he had before. The geometry is completely different, and because all the other jobs in the farm that are using your OTL are also picking the same definition in disk, all those jobs in the farm are going to have that update too, which means that the render is going to break. And by break, I don't mean that the Houdini file is going to crash or something like that. It's just that the renders are just going to look different. So you're going to have some frames that were rendered before the change on the definition that are going to look fine, and then you're going to have some other random frames that are going to pick the update and they're just going to look wrong. So user 1 is not going to be very happy that you did that modification on the OTL. User 2, because it's using the OTL open, well, that OTL is not picking that change from disk, so he is safe. But because he doesn't know that you did that modification, at some point he said, okay, you know what, I don't want to have that OTL open, I'm gonna match the current definition. And then there you go. He's got the same result. Now his file is also broken, and user 2 is not very happy too. Let's look at user 3. So user 3 was a little bit more adventurous, and he was not only keeping the OTL open, he was also adding something else to your OTL. If you were to modify the OTL, matching the current definition, what's going to happen is that he's going to lose that mountain because that mountain is not present on the definition that you created on disk. So he's going to lose that mountain. But what happens if he actually goes and saves that node type and then he matched the definition? Now the definition has a mountain, but it doesn't have the point jitter that you created. So if you sent your job to the farm and you didn't know that another user was actually modifying that OTL, what's going to happen is that now your file also looks like the file of user 3. So you lose the point jitter. Now your OTL doesn't look, or the result of the geometry doesn't look the same or as you expected. User 1, it's also upset because his geometry is looking different, and user 2, it's also mad because the geometry is basically not what he expected. So you can imagine that there's many problems that can happen if different users are working on the same OTL. And that's why pipelines tend to prevent this sort of issue by only allowing one user to work on an OTL at the time. Okay, so we're going to make the assumption that you actually need to modify the OTL because you think you can improve it, you can make it better. But the modification that you're going to do in your OTL is not going to change the final result. So I'm going to show you one example of that. Let's say that you just want to create a null inside. And you are creating this null because of some reason. You just think this null is going to make your OTL better, and then you save the node type. Then because you know that that change, that modification that you did is not going to modify the final result of the OTL, then you know that you are safe to save it because the other users are not going to have any problem because of that additional null that you put in there. So in that case, you could save the OTL. But if you are doing something like the point jitter that we did before, that you know are going to modify the output of the OTL, then what you need to do is save a new version of the OTL. So I'm going to go to digital asset, and then I'm going to increase major version. And you can see that it's telling you, I'm going to modify the OTL's name. I'm going to save from version 1, version 2. The library file name, you can leave it as it is. It's just going to create another one. Or you can tell it to use a custom one, and you tell it exactly where you want to save that definition. So if we look at where that OTL is saved, you can see that it's saved into your user preference folder, and then it's stored inside a definition called rbcreatePoints1. So what I'm going to do is I'm just going to save it on the same exact definition or on the same exact OTL, but it's going to be saved with a different name. And I'm going to click create. It's going to tell you that the library already exists. I'm going to click confirm. And once I did that, Houdini crashed for some reason. But I opened back Houdini, and you can see that now, if you select the OTL, on the same OTL file, you have two different definitions. If I keep definition 1, and then I go inside, you can see that your point jitter is not there. But if I go to definition 2, you can see that now the geometry changed, and the point jitter is there. The other users, though, are keeping the version 1 of the OTL. They don't get the definition 2 by default. If they wanted to change, because they think that your modification, it's useful for them, they can always choose the definition number 2 manually. But because that change doesn't happen automatically, it means that their jobs on the farm are not going to swap to definition number 2, and their jobs are not going to be broken. So always think, if your change on the OTL, it's going to change the final output, you have to save a new version. You don't want to become the guy who breaks everybody's job on the farm. Okay, the other aspect I wanted to mention was that modular OTLs are always better, at least in my opinion. And what I mean by that is that if you are doing a really long process, say for example you are destroying something, I'd rather have each one of the steps that is executed during that process as an individual OTL. So say for example, if you are fracturing, then you are creating constraints, then you are simulating, and then you are transforming the geometry after the simulation. I'd rather have each one of those things as something independent rather than having one single OTL that does all those 4 things together for you. And the reason I prefer that is because it's easier to control. Independent small OTLs are easier to maintain, and you can have different artists working on them at the same time. They are also faster, and sometimes big OTLs have things that you don't really need to use, and you have to pay the price of the time they take to cook just because they have so many things inside. So the way I think about creating creating setups is the same way I think about programming. When I'm programming and I'm creating a function, I want that function to create something very, very specific. And I want that function to do that action very well. And then I build my program by creating different functions, and each functions do something different. I don't create one function that do a lot of different things because it's very difficult to maintain and it's very difficult to explain to people how it works. So one example of that will be the create points. Even though this is extremely simple and I'm using it as an example, if I have an OTL that's called create points, I don't expect that OTL to do anything else, but you can see that the output are spheres, not points. So it immediately is just doing something that I don't expect that OTL to do. And the reason is because I have another OTL inside, so I'm gonna allow the editing of contents, and I have another OTL inside that do something completely different to what it's supposed to do. So what I would prefer rather than that is I will remove this OTL from there. I will save the node type. And remember, this is just an example. I already explained the risks of saving the OTL. And then I will just place that OTL outside the points to spheres OTL outside. And then I know that I have one OTL that creates points, and I have another OTL that generates spheres. In this case, that OTL was linked to the top level OTL, so it's blocking. But if you create the one that we created before, you can see that we have the expected result. And I would rather have two OTLs, each one doing something very specific, than one OTL that do both of those things at the same time. Although you are going to see big OTLs wherever you go to work, because usually when someone doesn't know Houdini very well, it's easier for them to use a big OTL than having to remember the name of the low-level OTLs. And the last thing, out of the top of my head, I think it's only expose parameters needed. Don't overcrowd your OTL with a lot of parameters that are not going to be used, because it just gets very complex. And when users see all those different parameters, they get overwhelmed very quickly. So when I'm creating my OTLs, I only expose what I think it's going to be very useful. If at some point I feel like, okay, these parameters, I will need it, but it's not exposed, what I do is I just create a new version of the OTL with that parameter exposed. One thing to keep in mind is that the topic on OTLs is quite big, and there's no way I can cover all that there is to know about OTLs in one single video. So if you want to learn more, what I will advise you to do is go into the Houdini documentation and just have a read at the digital assets set of tutorials, because they explain everything very well. One thing that I didn't explain, for example, it's the name convention for OTLs and what namespaces are and what branches are, but that is explained very well inside this documentation, so go ahead and have a read. What I'm gonna do in the next video is I'm gonna actually start working on the shots. I know this video was very long, but I hope you learned a little bit about OTLs and about good practices with them. So I'll see you in the next video. Bye. So the time has come finally to actually start working. So make sure that you open RB Spaceship Start HIP LC, or this is Houdini Indie. It's the one I use, but use whatever version you are using. I'm using also 19.5, so hopefully you are gonna be using the same one. And the first thing we're going to do is save a new file. I don't wanna, I just want you to keep start as its own file. I don't wanna work on this one, so let's go to file, save as, and then I'm gonna replace start with v1. Once you have done that, I'm gonna create a set of nodes here which are going to be used for the preparation of the geometry, as I did mention before. So I'm gonna create two geometry nodes. One, it's going to be called mprep, so it's going to be used for the environment preparation. I'm gonna copy it, and then this one, it's going to be called spaceship prep. Name says it's gonna be for the spaceship. I'm gonna select them both and press or hit Shift O on the keyboard. So that was Shift O, and then this kind of box, it's going to appear. And I use this to organize my scenes. And then I want a title here, so I will create a sticky note by clicking this button. That's gonna create this yellow square, and I'm gonna write the word geo prep. Actually the phrase geoprep. I'll right click on the title here, and I'm gonna set the size to medium. Let's change the size a little bit. Let's place it here, and then right click again on the title and then hide background. So then users know that this is the geo preparation, and then we're gonna do the same for the other nodes. Now when it comes for the environment prep, we're gonna be bringing the environment. So let's dive inside and let's create an object merge. I'm gonna use some sort of color nomenclature for my files. I tend to use purple for the object merges, and the first thing I do after creating an object merge, it's putting a name. So this is gonna be the merge environment. Just you know, we're gonna be bringing the environment here, but I'm also going to bring the spaceship, and I'll explain you in a second why I'm doing that. So let's go to the environment and copy. Basically, I'm gonna pick one of these guys. I'm gonna go for the high resolution. This is gonna be a bit slow, but I'm gonna go for the high one just because I want to keep the details from the ground. Basically, what I did is Ctrl+C, and then I'm gonna go to the object merge in the environment, and I'm gonna do Ctrl+V here. It's going to bring the environment, and as I said, it's fairly heavy. And usually what I like to do is set this to relative path. So then eventually, if you want to share this with another user, all the paths are relative. This is easier to place in other setups and so on. So now we have the environment here. I'm gonna bring the spaceship now. So let's go to ship, and let's go to let's do the same. Ctrl+C and Ctrl+V, and again relative path. And there you go, this is the spaceship. The reason I'm bringing both is because I want to basically keep only the part of the environment that it's close to the spaceship. And in order to do that, I need to have the spaceship in the same setup, because I'm gonna use the spaceship to cut a part of the environment. We know that this is a packed geometry, so I'm gonna unpack it. Every time when I unpack, I make sure that I keep the path attribute, even though I did mention that the path of this environment, it's not going to be used. And then what I'm gonna do is I'll pick a few frames of the spaceship. I'm gonna pick the frame when the shot it's starting, and a frame when the shot it's ending. And I'm gonna use those two frames to create a bounding box, and I'm gonna use that bounding box to cut the environment. So let's do that now. So I'll do a time shift. This time shift is going to be the first frame, so I'll do F start, and this time shift is going to be the final frame, so this is going to be F end. And now we have the spaceship at the end, the spaceship at the beginning. I'm going to merge them together. From that merge, I'm going to create a bounding box. So this bounding box contains most of the animation of the spaceship. I'm pretty sure it's not the whole thing. If you know that the spaceship it's moving in a weird kind of erratical path, I wouldn't just use two, but I know this spaceship it's moving almost in one straight line, so I'm gonna keep these two. But what I want to do is extend this bounding box so it uses more of the space. So I'm gonna use 50 and 50, 10 and 10, and 50 and 50, and this hopefully it's gonna give us the most of the space that we're going to be using. So the next thing I want to do is use a boolean to actually cut the geometry of the environment. So let's create a boolean here. Connect this to the environment and this to the bounding box. Just be a little bit patient, because as I mentioned before, this environment it's very heavy. Houdini might crash a few times, just be patient with it. And another thing I should have done before I plug the boolean into the environment, I should have changed this to manual. And that's something I usually do when I'm doing heavy processes, just because I don't want Houdini to be cooking this every time I change a connection or every time I change a parameter. I tend to do these changes with manual activated. So I'm just gonna pause until this cooks. No, I actually crashed. So I'm just gonna open Houdini back, and I'll see you in 1 minute. So we are back in business. I changed this to manual, and I'm gonna plug this here, and let's set this up so we can basically cut a piece of the environment. On the boolean, I'm gonna set the first one as surface, because we know the environment it's a surface. I'm gonna keep the other exactly the same, and I want to keep the piece of the environment that it's inside the bound. So for that, I'm gonna set this parameter to intersect. I don't wanna triangulate anything, so I'm gonna set this to no polygons. That's it pretty much. I don't wanna change anything else. So I'm saving the scene, and hopefully this is going to work. Okay, so it took some time to cook, but that was expected, and this is what we get. The part of the environment that it's inside of the box. But now we want exact opposite of this thing. So what I'm gonna do is I'm gonna set this to manual again. I'm gonna copy and paste this here to my right. In this case, we need to kind of change some of the parameters. So instead of the intersection, I want to subtract because I want to subtract this piece from the environment, and that's pretty much it. I'm gonna later merge these two as one single mesh, but because I want to be able to separate them later, I want to put each one of these guys in one group. So I'm gonna create one group here, and this group it's going to be called intersection. It's gonna be on the primitives, and it's gonna group them all, and this is going to be not the intersection but the subtraction. And now we know later that if we want to separate a piece of the environment, we just need to keep the intersection or the subtraction, and then I want to merge them together. I'll create an output, and something I like to do is to put this thing into a sub network, just because I don't want to be, I want my scenes to be kind of clean, and I know that I could select these nodes and basically hit on the keyboard Shift C, and that's going to create a subnetwork from the nodes that I had selected. And I'm going to call this Boolean split. We know that the input 1 is connected on the first input, and the input 2 it's connected into the second input. That's correct. So we know that this is still working, and we want to cache this node, or actually the result of this node. I'm not going to change this to auto update because I know this is going to be slow. I mean just one boolean took almost like 2 minutes, so I'm not gonna auto update now. What I want to do is create a cache and cache this out. And something I didn't mention before is that in this set of videos we are going to be using a labs node called file cache, but we're not going to be using the first option. We're going to be using the labs file cache, but I'm going to explain in the next video why we are going to be using this. I find this is a great node. Since version 19.5 we started having these problems. I'm not sure if it's a bug with Houdini, with the node, or with my installation, but just we won't pay attention to this. I'm gonna plug this here, and in the next video I'm gonna explain why I'm using this, what wedging is, some of these advanced parameters. And because we are gonna be updating this node every time we created one, we are gonna use a little bit of Python to update these parameters by creating a shelf tool that we're going to be using every time we create a file cache. So I'll see you on the next one. Bye. Okay, so let me talk a little bit about this file cache. You might be familiar with the file cache that comes usually with Houdini, but this is a wrapper of this one that comes with labs. The main difference is that it has some new functionalities that really help when you are doing effects, especially at home. One of those functionalities is the wedging option here, which let you do variations, let you randomize parameters, lets you create or cache different jobs in parallel in one machine. This is extremely useful, and we will be using this a lot along the workshop. Another thing I like is that the base name is set to $OS by default, so you don't have to change that, while the file cache, the normal one, has this heap name there, and I don't really like that because the name end up being really long. So we won't be using the normal file cache, we will be using the labs file cache. There's a few things though that I like to change on this node every time I use it. One is that I don't leave this parameter as $OS. I always add something else. And the main reason is that if I leave as $OS this parameter, this will be replaced with the name of the node, which means that if I have one of these nodes somewhere else with the same name, I risk that node is gonna override whatever I cached here. So I always tend to add to this string here the name of my parent node. And you can do that by putting this inside backticks. And then I put lowercase, whatever that symbol is called, I don't remember. And then put backtick again, up name. And then you point basically to the parent node, which it's gonna be called mprep, and then you put brackets and backtick. This string is gonna join together the name of your current node and the name of your parent node, and this is gonna be safer when it comes to caching, because it's less likely that you're gonna find another name or another node with the same name that's under a parent that has the same name. It might happen, but it's less likely. So that's it for this node, and then you can basically change the name of this to whatever name you want to use. In this case I want to use environment split, and then you can press cache. As you know already, this is gonna be very slow. It's gonna take probably 2 minutes because it has to do that boolean on the heavy environment, so I'm not gonna cache it just yet. Something else I want to do is that since I'm gonna be changing this all the time, I might forget doing it one time or like a few times during the project. So I want to automate this thing, or at least make it easy for me to do it every time. And for that, we are going to do Python. We are going to create a shelf tool it's going to allow us to change this. Another thing I forgot is that if you go to advanced, you will see this harden base name on save. And what this do is that every time you click save here, it's going to replace this string for whatever it's evaluating to. So it's gonna replace that expression that you put there for this. And then you might end up with the same problem. You might end up like having caches overwritten. So I don't like that. I don't like this option. It's a personal opinion. You might keep it, but I'm gonna also change this to 0. Okay, so let's keep it as it is by default for now, and let's make this the same as it is by default for now, also for now. And what we're gonna do now is create a shelf tool. So if you have your shelf tools open, what you need to do to create a new one is press this plus button, and then you can do new shelf. And then this new shelf, it's going to be saved on your user folder on whatever version of Houdini you have currently installed. There's gonna be a toolbar folder, and then the shelf, it's gonna be called default shelf. I will create my new shelf there, but there's options to create custom shelves on custom folders, but it gets a little bit more complicated, and I'm not gonna get into that. The name of the shelf, it's gonna be Rebelway, and the label, it's gonna be the same but with uppercase R. And let's do apply. So now we have this shelf tool. The next thing we need to do is right click and do new tool, and this is gonna give us this pop-up where we can put the name of the new shelf tool, the label, and one icon. So let's do that. I'm gonna call this tool fix labs cache, fix labs cache, and I want to have an icon for the tool, otherwise it's gonna keep this H, and I want to use the same icon as the labs file cache. So I'm gonna right click on the node, type properties, and then it brings the operator type properties. Then you have a look here at the icon string, and you can copy this. So Control C, you can close this now, and then Control V here and press apply, and you can see that the icon changed. So now we have our first shelf tool for the Rebelway toolbar. Then you can go to script, and here we are gonna write our Python script. Now this is not a tutorial about Python, so I'm not gonna go into like what a class is, what each one of the methods of that class is. So I'm gonna copy and paste the code here. I'm gonna explain you what each line do, and then hopefully that's gonna help you. If you are really interested into learning Python, there's another Rebelway course into Python that goes really deep into every one of these things. So the first line here, import who, it's bringing the Houdini module, which is the module that contains all the Python functionality or API for Houdini. Then the next thing we are doing is I'm creating one variable called labs node, which it's storing all the nodes that I have selected. So who.selected nodes, it's gonna give you a list of all the nodes that you have currently selected. So if I, for example, select this and then select this variable is gonna contain the Boolean split, and it's gonna contain the environment split. So what I'm doing here is checking if I have any node selected in this variable, then do whatever it's after the if. So if I don't have any node selected, this is not going to happen, and it's going to do whatever it's on the else, and this is basically showing a message. So I'm gonna show you one thing that I'm pretty sure you will find very useful when it comes to learning Python. If you press Alt Shift P, you will bring the Python shell, and then in here you can do who dot, and then it's gonna show you a bunch of methods. I will suggest you to read the help for this, but for now I'm just gonna bring the UI module, and then I'll bring one method inside that module called display message. And then I'm gonna show whatever, like hi there. And I click enter, and you can see that this is the UI displayed by the display message. And then you have options for buttons and everything, but I'm not gonna use that for now. I just want to show a message when you click this tool and there's no node selected. Okay, so then what this is doing is that for each one of those nodes that I selected and it's stored in this variable, it's going to check if the name of the node, and I don't mean the name of the node here, I mean the name type of the node. So if you want to know that what's the type name of a node, you just need to middle click here. It's like what you do when you want to see the parameters, the attributes. Middle click on the node, and then in here you can see that the type name of the node, it's labs column file cache column 2.0. If I do the same here, you can see that this is subnet, and if I do that here, you can see that this is unpack. So we need to make sure that whatever node we have in this list, it's a labs file cache, because otherwise this is going to try to find this parameter called base name, and because we are going to try to change this, and we're going to try to change this. If you try to change these parameters in a node that doesn't have it, like this one, then we're going to get an error. And what we want to do is avoid those errors. So I'm checking if the node type name of this node contains this string. Another useful thing that I always do is that I create one variable here. You can call it node, for example, and then you can drag. I always do right click, always on top, so this doesn't get hidden, and then I drag this thing into the shell, and you can see that it's giving me the full path of the node together with the Python methods to access the node, and then you can hit enter, and then if you write node dot, and you will see all the methods that you can access, and you can have a look at all of them. Most of them are extremely useful, so really have a look. But what I want to show you is that if you do node.type.name, you will see exactly the same thing as we were seeing when I middle click on the node. So that's what I'm doing here. I'm basically checking if this string up to file cache, so without using this part, because maybe they could create a new version which is 3.0, and I want this to work with all the versions. So I want to see if this string here, it's present on the type name of the node, and if it is, then I'm gonna have a look at the parameters and change them. So in here I'm accessing to the current node, which is the node the current node of the for loop. So you can see here that we are doing that for node in labs node. So for every node inside this labs node, I'm gonna access the parameter called base name. And one way you can know the name of the parameter is by hovering your mouse over the parameter, and you can see that below it says parameter base name, and that's how I find the names of the parameters often. And then I want to set this parameter to this string, which is the same string that I showed you before, that joins the name of this node with the name of this parent node. So I'm basically setting that to this string. This is going to replace $OS with this string here. And then next, after that, I'm setting this parameter, the hardened base name on save. And again, if you hover your mouse over it, you will see that it says hardened base name for the name of the parameter. So I'm setting that parameter to 0, right? Because I want to turn this off. So off it's 0, on it's 1. And that's it. So if this node doesn't contain this labs file cache on its type name, then I don't want to do anything. I want to continue and go to the next node. That's in case you select, for example, one file cache, one boolean split, and maybe another file cache. It's gonna work on the 2 file caches, but it's not gonna do anything on this boolean split, and it's not going to give you any error. So after you copy this there exactly as it is, press apply and then accept. And then what should happen is that if you select this node and then you click this shelf, it should change this, but it didn't because I think it was in manual. But now you can see if you change this to auto update, it's doing it. So if you click this, it should work. Just to make sure 100% it's working, let's create another labs file cache and let's have a look. If I select this and click here, you should see that this is replaced and then this is untick. So that's pretty much all we need. So let's click on accept. And now what I will do is that I'm gonna cache this out. So I want to untick this time dependence cache because this is a static geometry. I don't want to cache any frame or any frame range, which is the default. It's basically the default option. So I'm gonna untick this and then I'm gonna hit save to disk. And I'll do that after pausing the record, just because this is gonna take some time, and I'll be back in 1 minute. Okay, so the cache is done. Just be a bit patient because it's gonna take some time. And then I'm gonna place a split sub. And if you remember correctly, we had 2 groups here, so I'm gonna use that group to separate the geometry. So I'm gonna keep the intersection group on the left. So that's gonna go here, and the subtraction group on the other side. So if you remember, we had intersection and subtraction. I'm gonna create two nulls, and this is gonna be out M for ship. If you remember correctly, we have the spaceship crashing against the ground. So this is the area of the environment that we are going to use for that collision, which is directly below the ground, the spaceship. And we're gonna copy and paste this, connect it to the second output, and that's gonna give us the second piece of geometry, which is the outer geometry, as you can see here. I'm gonna call this out-env no ship. And I'm warning you now, I don't have a lot of imagination for names, so just bear with me, or use whatever name you think it's cooler than this. I'm gonna delete the groups now, so I'm gonna do a group delete, and I'll delete everything, and I'll delete everything. Now you might be wondering, why did I basically merge the geometry here if I'm gonna split it here? And the reason is because I like to cache, use as little amount of file caches as I can. So rather than having two file caches here, one for each part of the geometry, I have one and then I split it, but you can do the other way too. That's gonna work. So that's basically it for the preparation of our environment. Now we created our Rebelway shelf tool, and we are ready to start working on the preparation of the spaceship, which is gonna be a little bit more involved. So I'll see you on that one. Hey guys, so I decided that I was going to make a bonus video because I saw some of you had some problems with the file labs cache, and I just wanted to explain how to use wedging. So I'm just planning to give you two options. One is showing you how to use wedging with the normal PDG workflow and the file cache node, which is the normal file node that comes with side effects without labs. And another option, which is going to be using the actual labs cache. I'm going to show you what the differences are and how to do wedging with both of them. And in this case, what I'm doing, just as an example, is an explosion. And you can see that each wedge has a different explosion in a different RBD simulation. It's going to be very simple, so I hope this is helpful for you. What you're gonna see, it's a new file called Wedging Start. I'm gonna leave it somewhere on the week 1 resources, so make sure you download it. And what you will see there, it's a file that contains 3 geometry nodes: the sources, the explosions, and the RBDs. And then inside the sources, you will see we have a point sub that is creating 6 points, and then an explosion ID, which is creating an explosion ID attribute for each point number. Then a blast sub, which is keeping an explosion ID by using an attribute that we're going to create later, which is going to be based on wedges. So we're going to have 6 wedges, and each wedge is going to have its own number. You're going to see that later. Then I have a pyro burst source, which is going to create our source for the explosion. And I'm just creating a volume rasterized attributes to convert those points into volumes. Next, on the explosions, we have a very simple pyro solver. I'm merging the fields that we created before. I'm running a simulation, and then I'm just gonna cache that explosion. And then finally, on the RBDs, we have a circle. I'm extruding the circle, creating some normals and some points, fracturing the circle, configuring the pack geometry, and setting some points to active, basically the points that are inside a circle, using a group sub. And all the points that are inside that group, I'm setting them to active 1, and everything else it's active 0. I'm bringing the fields of our explosion, of the source of the explosion, and then I'm using those fields to drive the velocity of a very simple bullet simulation here inside a subsolver, where I'm bringing the fields, I'm deleting everything but the velocity, and then I'm adding the velocity of the field to my current velocity inside a point wrangler. If you don't understand what's going on here, don't worry. I'm gonna go into detail into what these things are doing in future weeks, but for now what matters is the actual wedging. So let's go ahead and rename the file. I'm gonna call it PDG version 1. Let's go into the sources, and then after the null, let's create a file node. I'm gonna call it explosion source PDG. And I'm gonna call it PDG because later we're gonna also do the option with the labs cache, and I'm gonna basically change the name. Okay, so I want to set the explosion cache to automatic. So if there's any file already in disk, it's not gonna do anything. If there's no files in disk, it's gonna cache them. And basically that's gonna save you some headaches. You can also set it manually to read or write. That's up to you. So I'm gonna create the file node for each one of the simulations. Let's go into the explosions setup. And then after the null, let's create a file node, and I'm gonna rename it to explosion sim PDG. And now go into the RBDs, and let's do the same here. I'm gonna call this one RBD cache PDG. Okay, cool. So now what I want to do is basically change the wedging explosion attribute using PDG. So I'm gonna go back to the object level, and I'm gonna create a top network. The first example is gonna use the normal vanilla PDG. So in case you don't want to use the labs file cache, you still have the option to create wedges on your own. So let's go inside the top network. You're gonna see a local scheduler. By default, it's setting the working directory to heap. That's what I'm gonna use. But if you are working on a render farm or a company that has a render farm, it's very likely that they're gonna have their own local scheduler if they are working with tops. So let's leave this as it is. And for now, what I want to do is create a wedge top. And this is the one that's gonna initialize the wedging attributes that we are going to need. So we have 6 points for the explosions. We need to have 6 explosions. So I'm gonna set the wedge count to 6. And if you right click on the wedging node and generate the node, you're gonna see that we have 6 different working items. You can double click on each working item and you're gonna get the pop-up that's gonna give you the information, or what I usually do is that I just middle click on each one, and that's gonna show me very quickly the information. So you can see that each one of the working items have a wedge index and a wedge num. This is going to be important because wedge num, it's gonna get repeated for every single wedge. In this case, we are gonna have 6 different wedge nums, which goes from 0 to 5. But once you start creating other nodes that depend on each one of the wedges, you're gonna have many more working items, and what's gonna happen is that the wedge num is gonna keep repeating for each one of the wedges, but the wedge index, it's always going to be unique. So when we're gonna create the caches, we're gonna use the wedge index to create the path for those caches, and I'm gonna show you that in a minute. Let's first create the attributes that we need. First, as you already saw here in the sources, we need an explosion attribute. But also in the explosion, here in the pyro solver, if you go to the shape and open the disturbance tab, you can see that I'm using a disturbance attribute here. And in the turbulence, I'm using a turbulence attribute. This is just an example. You can go ahead and wedge any other attribute you want. And the RBDs, I'm not wedging or modifying anything here. This is set as it is by default. So let's go back into the top network, and I'm gonna start creating the attributes. Let's hit the plus button here, and I'm gonna create an attribute name that I'm gonna call explosion. And I want the explosion to be an integer, so I'm gonna change the value type to integer, and I want to have a range between 0 to 6. Now, if you middle click, you're gonna see that that attribute still doesn't exist. In order to for the attribute to exist, you need to tell the node that it needs to be generated. And you can see that now we have an explosion attribute that goes from 0 to 6. Now I want to create another attribute, which I'm gonna call turbulence. It is going to be a float, but I want to show you another example which I'm gonna do by adding a value list as the wedge type. And in this case, I want to set 6 different values that I'm gonna explicitly set by using these parameters. So the first one is gonna be 1, second one is gonna be 15, third one is gonna be 0.1, then the fourth one 2, 10, and 6. So what you should see once you generate the node is that you're gonna have a turbulence attribute that's gonna specifically use the values that you set there. So this is a very good way to set specific values. So say for example you wanna test how the explosion looks by setting the density or the turbulence or whatever parameter you want to some specific values. You can create this list in this way rather than using random samples. I'm gonna create a last attribute which I'm gonna call disturbance. And disturbance, I'm gonna just use a range between 0 to 6. I'm gonna generate the node, and you can see that now I have disturbance also as an attribute. And in this case, it is a float rather than an integer. Okay, so now we have the wedging. And what we are going to do next is we're gonna cache the geometry. So in order to cache the geometry, you need to create a rough geometry node. And this rough geometry node needs to point to the geometry that it has to cache. So I'm gonna jump back into the sources, and then I'm gonna select the null. Now keep in mind that this might be confusing. You might think that you need to point to the caching node, but this caching node doesn't have any geometry because it hasn't cached anything. You need to actually point the fetch node in tops to the null that contains the geometry. So make sure that you select the out fields, Control C. Let's go back, and then in the rough geometry, I'm just gonna point to it. I'm gonna rename the fetch node to source out. Here comes the most important thing. First, the evaluating using needs to be set to frame range because we are going to cache 100 frames. This is important because if you set it to single frame, of course, it's gonna set cache only 1 frame. But keep this in mind because later I'm gonna show you that even by using single frame, some nodes are gonna inherit the attributes from the parameters from the parent node or the node that it's connected to them. So keep this in mind. I'm gonna talk a little bit more about this later. The second thing, and one of the reasons I find this workflow annoying and the main reason I prefer the file labs cache, is that you need to set the output file on your own. So what I'm going to do is I'm gonna add a folder which I'm gonna call $OS. So basically on the next to the heap file, we're gonna create a folder that's gonna be called source out. Inside that folder, I'm gonna create a geo folder, and then inside there, I'm gonna call the cache source out. So that's what this $OS is doing. Dot the frame and then bgo source. But the problem is that we have wedges, right? So if you don't specify on the path the different wedge index, then what you're gonna say is that each wedge is gonna overwrite the previous wedge. So remember that each one of the wedges is setting an attribute called wedge index. And that's what I'm gonna use here on the path. So next to the $OS, I'm just gonna add a backtick, and then I'm gonna write wedge index. Make sure you are spelling it correctly, otherwise it's not going to work. And you can see that it's adding the number of the wedge, but I made a mistake. I forgot to put 1 dot there, so I'm gonna do it now before the $OF. And now you can see that it has the number of the wedge and then the number of the frame. Something else I realized is that actually I wanna put all my caches inside a folder called geo. And then inside the folder geo, I wanna create another folder called source out. So make sure that you copy this name convention, and this should cache the source into the proper folder. Okay, so now let's go to a rob fetch, and in the rob fetch, what I want to do is set the caching mode to write files. So we make sure that it's writing the files. You can set it to automatic, and again, what's gonna happen is that if the files already exist in disk, it's not gonna try to cache them. But in this case, I just wanna force the writing of the files. And the next thing I want to do is that I'm gonna use 10 frames per batch, and what this is going to effectively do is that when it's triggering the Houdini session under the hood, that's gonna run these jobs, rather than running one single work item, it's gonna run 10 work items and then it's gonna get closed. Then we're gonna open a new session of Houdini. It's gonna run another 10 work items, and so on and so on. And what you are gonna get in this case is that because you are not having to open Houdini every time you run a work item, then your job is gonna run faster. Keep in mind that if your file is very slow to open, then that's gonna add to the time that you need to wait. So that's why it's better to run a few frames per Houdini session rather than 1 frame per Houdini session. And locally, this is not that important, but when you're working in a render farm, this actually it's very important. Okay, so now we have the source out and the frames per batch set. This should be ready now. So what I'm going to do is basically take the output file. I'm gonna copy the parameter. I'm gonna jump back into my sources and then select the explosion source PDG, and let's copy or paste that parameter in here. So what's gonna happen is that the caching is going to be done by the ROP geometry output, and then it's gonna be read by the explosion source. So you could go ahead now and generate the node and cook and everything, but I'm not gonna do it now. I'm gonna carry on with the other nodes. So now we are gonna set the parameters for the explosions in PDG. So let's go back to the top network and let's create another ROP geometry output. I'm gonna call this one explosion out. So let's do the same. Let's go back into the explosions network, select the null, go back into the top net, paste the null into the subpath, and then let's update the output file. And I'm gonna do that by basically copying the same expression that we used before. I'm gonna use exactly the same, but keep in mind that in this case I'm not gonna evaluate using a frame range. I'm gonna evaluate using single frame. This is possible because when you have a node connected to another node, this one is gonna recognize that in here we are caching a frame range, and this is gonna behave accordingly. So if I generate this node, you will see that we are generating 1 work item in here for every work item here. So this is gonna work accordingly. Another important thing, if you go to a ROP fetch, is that of course I'm gonna set the cache mode to write files, but I'm gonna set the all frames in one batch to on. What this is gonna guarantee is that we're gonna run the cache as a simulation. And this is extremely important because remember, the pyro simulation has time dependency. Every single frame depends on the previous frame. So you cannot really go to the last frame and cache it, because you need to cache all the previous frames before that frame can be cached. So make sure you have the all frames in one batch set to on when it is a simulation. Let's go ahead and copy the output file to my explosions cache. And finally, we're gonna do the same for the RBD. So let's dive inside and copy the null. And let's generate another ROP geometry. I'm gonna call this one RBD out. And let's copy the subpath. Again, it's gonna be a single frame. I'm gonna copy the expression. And then in the ROP fetch, let's set it to write files and all frames in one batch, because this is gonna be an RBD simulation. And let's generate the node. And you can see that we have the nodes generated. I think what you are seeing here, basically some of the work items are already cached, is because when I was generating the examples, I was using the same names. So these files already exist on disk. So just to show you that you can delete those files, I'm gonna right click and then hit delete these nodes output from disk, and you can see that I already had all those files cached. So I'm just gonna go ahead and select them all and delete them. And I'm gonna do the same here. I'm sorry about that, I just forgot to delete them before recording this video. So now we should have an empty template. Okay, so now we have all the nodes. I'm gonna generate the last one. And then if you start clicking on each one of these guys, you're gonna see that it basically is linking to the respective work item above. And if you click one of these guys, it's gonna basically link to all the respective nodes below. As you can see. Sometimes if you don't see that, for example, before you saw that we weren't seeing the work items, it's because I was in a different page. But if you go to the proper page, you know that in all of them we are in the page 1, then you can see the connection, it's working. So now you can see that we are not seeing anything. That's because we are basically running out of work items for the page. So you have to basically go to the next page until you find the proper ones. Okay, so now we have all that we need. And let me go back through the file just to explain what's going to happen. We're going to initialize the wedging attributes here. We're going to initialize disturbance, turbulence, and explosion. And remember, you can middle click in each one of them just to see what the values are. And then once those values are initialized, they are going to be used by your expressions. So the first wedge is going to delete all the points by the current explosion. So you are going to end up with 1 point, but you had 6 before. So we are going to cache 1 explosion per wedge, and we're going to cache 1 RBD simulation per wedge. So let's go back to the top network, and I'm going to run the cache. So in order to do that, I'm going to right click on the last one, and then I'm going to dirty and cook this node. And what you should see is that you're going to start caching the sources. It depends on the velocity of your computer, how strong it is. You can see that because I deleted all the files, then you're basically caching everything, which is not that slow because obviously that sourcing is not very heavy. I'm using very low res volumes. And once you cache the sourcing, it's going to start caching the explosion, and then it's going to start caching the RBD out. Remember, it's going to wait for these caches because we set the explosion out to all frames in one batch. So it's going to basically wait. If you want to explicitly force the wait, you can also create a wait for all node and put it here. So what's going to happen is that it's going to wait for all the nodes or work items to be done. But in this case, I don't want to, because say, for example, you finish caching one of the wedges for the sourcing, and this node can actually start caching one of the simulations once its own sources are already done. So you don't really have to wait for this whole set of wedges to be done before this one starts, if that makes sense. So I'm gonna let this run, and I'll be back in 1 moment. Okay, so it's done. What I'm going to do is I'm gonna copy the RBD output file, because I actually forgot to point my file cache to that one. So let's make sure that you paste the relative reference there. I didn't do that before. And now we should have an RBD simulation, we should have an explosion, and each one should be controlled by a different wedge. So let's have a look. You can see that when I start looking at different wedges, we have different results. And you can see that also definitely the turbulence and the disturbance, it's different for each one of them. So this could be one way that you could run different wedges, and then you can use these caches in any way you want. You could instance them, you could copy them, do whatever you want. Of course, the explosion looks terribly bad, but it's up to you to make them look better. So we have this working with the normal PDG approach. What I'm going to do now is I'm just going to save this file to PDG version 1. Now I'm gonna save a new version, which I'm gonna call labs version 1. And inside the labs one, I'm gonna delete the topnet because we're gonna use a different approach. In the sources, I'm just gonna create a labs file cache. I'm gonna copy the same name, delete the file cache, replace the name, and I'm gonna replace the name PDG with labs. I'm gonna fix the node just as we have been doing so far. Make sure that load from this is on. If not, then it's not going to work. The wedging is not going to work. It needs to be on. Then I'm just gonna copy this node. I'm gonna go into explosions. I'm gonna paste it here, and let's replace the name. Cool. Make sure this one is set to simulation. Let's go into the RBDs, paste it here. Let's replace the name. And also make sure this one is a simulation. And let's go into the sources, and this one is not a simulation, so turn that off. And we also need to set the wedging attributes, because before we were setting them inside a wedge node. Now we need to set them into the actual file cache. Now, something that is confusing is that you might think, and I was actually thinking before, that I need to set the attributes in all of them. But because all the files are gonna contain the same wedging attribute, once it is created, then we don't really need to set the wedging attributes in all of the different file caches, or at least I don't think so. If I realize that this is needed, I'm gonna update this video later. But for now, I'm seeing that I don't really need to create the wedging attributes on all the file caches. I'm just gonna do it on one of them. But if you prefer, just do it on all of them. So let's go ahead and activate the wedging tab. Then in all wedges, I'm just gonna set the wedges to 6. And I'm gonna add 3 different attributes. The first one, again, was explosion. And explosion, it's going to be a custom range. That's gonna go from 0 to 6, just as we did before. Second attribute is gonna be turbulence. And in this case, it's gonna be a specific sequence or specific values. We don't have the same option that we had before, but in this case we can set the list of values by basically giving all the values separated with a white space or an empty space. So I'm using the same values that we had before. And finally, we have an attribute called disturbance, which is also going to be a custom range that goes from 0 to 6. Cool. All right, so now we are setting those attributes, and because we already have everything set here, it should immediately set the explosion ID to the proper value. And Houdini just crashed when I tried to do that. And you can see that now the work items are gone, which means that this thing is not going to evaluate to anything. And sometimes when you close the scene and you open it, you're going to see that this is happening. So what you need to make sure is that you toggle on and off the wedging, and then you're good to go. And now you can see that we are actually getting a value. Something that's worth mentioning is that I don't see any option here to set the values to integers. Maybe I'm just being stupid and I don't see them. Or I could just use a specific set of values like I'm doing here. But what I'm gonna do just to force this to be an integer is I'm gonna use an int function just to convert the explosion to an integer. And you can see that now we have as value 2. And we are actually having 1 point here. Okay, so now we have all the attributes that we need. And we have a wedge count of 6. I'm gonna go and get into my explosion setup. And in here in the explosion, I'm gonna also activate the wedging, set it to 6. I'm not gonna set the attributes because they should already exist and be created by the previous caching node. And then in here, I'm gonna do the same. Cool, so let's select the RBD Cache Labs and click the Add button on all of them. And that should create a top network. If you dive inside, you have all the nodes that we need. I'm gonna put them in order. The first one should be the sourcing. So it's this one. Second one should be the explosion, and then last one should be the cache of the RBD simulation. So now if I generate this node, you should see that all the proper work items are created. The wedging is not needed this time because it's created actually inside each one of the file labs caches. So if you dive inside there, you will see that there is a top network inside and all the wedges and everything is generated inside. So you don't really need to worry about that. And also, what's very cool about this node is that it's gonna let you load either all the wedges or specific wedges. When you have this off, what's going to happen is that it's going to load the current wedge, which is great because you don't really have to do anything here. But if you want to load all the wedges together, you just need to activate the wedges to merge and it's going to load them all. And something that I also like is that if you go to the advanced tab, you can see that in the path construction, it's using the wedge index, wedge string, and all that stuff to generate a folder for each wedge. So you won't have all the geometry put inside the same folder. You could do that also with the approach that we used before by using the wedge index attribute to generate a folder. But it just becomes a pain because then you have to also create your own file cache node to load the geometry from each wedge, while in here you have a for loop that does it for you. If you want, you can also have a look at this for loop and try to build your own. It's up to you. I'm just gonna use this node because I feel like it's very easy to use. It's kind of buggy in a sense, but it's similar to also to the caching node that we have at ILM, so I kind of like it. Okay, so now what I'm going to do is gonna go to the top network, and then I'm gonna right click. I'm just gonna make sure that we don't have any geometry already cached from my previous files. You can see we have. So I'm just gonna go ahead and remove them. Same here. So let's generate the nodes, and then what I'm going to do is just dirty and cook this node, and that's gonna start generating everything that we need in the same way that we did before. So I'm gonna pause the video and I'll be back in one moment once this is done. Okay, so the caches are done. Let me activate the RBDs and the explosions. And you can see that we are getting the same result that we had before. So let me go into the sources, but first let's make sure that the viewport is stuck to the object level. And then from here, I'm just gonna change two different wedges. And you can see that we're getting a different explosion, but for some reason the RBDs are not changing. So let's go into the RBDs, and yeah, it's because we are not activating and displaying the actual cache. So yeah, there you go. So here you have a way to create different explosions. And then if I have some time, maybe I can create a bonus on how to use these different caches with instancing, and how to use pack disk files and their intrinsic attributes to load different frames at render time. But for now, I think this should help you with the wedging. Keep in mind that every time you close Houdini and open it, you're gonna need to restart the wedges. So make sure that you toggle on and off the wedges. You could also create a Python shell for that. That's gonna basically restart all the wedges of all the instances of this node that are in your scene. But for now, just go ahead and do it manually. And that's pretty much it. That's all I wanted to explain about the wedging. This is a basic example. I'm gonna make sure that the file is fixed when I uploaded it, and I hope it's useful. So I'll see you in the next video. Bye. Okay, so let's go up one level, and now we are going to go into the Spaceship prep. So before we do that, let's save a new version. File, save as version 2. Let's go into this ship out node, copy. So Control C, and then let's go here and create an object merge. I'm gonna make it purple, and let's call this merge ship. Let's paste the path here and make it relative. So if you make this, change this from manual to auto update, you should see the spaceship here. There's a few considerations we need to have when it comes to animated objects. So imagine you are destroying a building. A building, it's a bit easier because the building isn't moving, right? Unless it's a guided simulation for a building, but that's not the topic of today. Usually a static object, it's easier to break because you don't have to consider the position of the object, whether it's moving or not. But in this case, we have a moving spaceship, which is going to make things a little bit more difficult. Now, the first thing I look into when I'm receiving an animation, especially an alembic, is I have a look and see if there's any transform information that contains the translation and rotation of this object. And often we have that information in the alembic. So I'm gonna have a look. I know for a fact that we don't have it here, but I'm gonna show you how I check that. So you go to the primitive option here, make sure that you have selected the spaceship, and then you go, I'm gonna hide this. And then I'm going to the intrinsics, and these intrinsics are a bunch of attributes that are intrinsic to this type of object, which in this case is a packed alembic. So you can have a look at these ones and see what you have, what the value it's gonna give you. So just for fun, let's let's choose any of these. So let's do file name. And as you can see, the intrinsic ABC file name, it's giving you the full path to the Alembic on disk. But these things are very useful because you could, for example, replace this for another path and do crazy stuff like showing low-res geometry on the viewport, but then at render time maybe changing this intrinsic value for another geometry, which is the high res. Yeah, you can do things like that. But in this case, we don't want to change that. We want to have a look at the packed full transform. And you can see there is a matrix there, which it's a 4x4 or a 16 matrix. And that matrix is not changing, which means that when this spaceship was cached, the transformation information wasn't stored as part of the Alembic. Another way I have a look at that is by having a look at the transform, which contains the scale and the rotation. And as you can see, it's also an identity matrix, which it's kind of cool because it means that this is not a scale or like we won't have any problems with the scale or anything like that. But the downside of that is that we will have to compute or calculate that transformation ourselves. Why do we need a transformation? Because we are going to be fracturing this spaceship, and then if you fracture that spaceship as it is, say if you scatter some points and then you do a Voronoi fracture, because the spaceship is moving all the time, that scatter is going to change, the Voronoi fracture it's going to be recomputed, and this is going to be complete chaos, and we don't want that. That's not going to work. So what we need to do is make the spaceship static, so keep it, for example, in one of the frames, usually the first frame. Some people will also send it to the origin, fracture there, and then send it back. I don't like that approach. I used to use that approach, but not anymore, because it gives you transforms that are not clean, which I'm going to explain in once we get to that. But what I do now is that I keep the spaceship on the first frame, or any useful frame for that matter. I fracture there, and then I bring back the animation. And that's what we're going to do in this case. Before doing that, let's make sure we have everything set up for that. So I'm gonna do a time shift to keep the spaceship on the first frame. Let's change this to F start. Then this is a packed Alembic, so I need to unpack. Please remember to be saving your file all the time. Houdini tends to crash a lot, and you don't want to have to repeat steps. So I save every time I put a node, I save. On the unpack, make sure that you are transferring the path, because we are going to be using the path for plenty of things, so we know we are keeping it there. The name is empty, so for now I'm just going to attribute delete that name. So we only have the attributes we need, and we don't need all these detail attributes. I'm going to delete those detail attributes, and that way our geometry is cleaner. And if you middle click here, you can see that this is now it's a polygon geometry rather than a packed Alembic. Another thing I'm going to do is I'm going to force the normals to be recomputed. So I'm going to create a normal. And that normal, I'm going to basically change it until it looks kind of more like a hard geometry model. If you have a look at this, it looks soft. Like at some point the normals were broken. So I'm going to try to make them look similar to what they were at when I received the model, as on its static position in the origin. And I think 30 is gonna bring us closer to that. This looks better. And now what I'm going to do is extract that transformation matrix. That's the first thing I'm going to do, just because I want to use that transform to move all my fractures later. So I'll do that in an additional branch here on the right, so I can always access that matrix from anywhere else on my setup. So I'm gonna unpack the actually, I'm gonna unpack before the time shift. I'm gonna put the unpack here. Time shift, it's going to make sure that whatever comes down this stream, it's gonna keep the unpack only once. But on the right stream, we need this unpack to happen in every single frame. Then what I'm going to do is blast some geometry. And what I need to select is a piece of geometry that kind of makes sense. I mean, you could select any of them, any part of the spaceship, but I'm gonna select one part here on the center by using the path attribute. So I'm gonna press 9 on the keyboard, go to this little symbol here, and then I go to Alembic path, and then I'm gonna select one of these parts, and then I need to do this in the blast though. So I'm gonna select the blast, hit this little arrow here. Remember, if you don't see this list here, press 9, That's gonna bring the list, and then select one of these pieces and hit enter, and that's gonna select by path, which is what you are seeing here. So I'm gonna use this to create the matrix. So I'm gonna delete non-selected, and now we only have this piece. And something I used to do was create the matrix using Vex, but these days you don't really need to do that because we have a really cool node called extract transform, which we are going to be using. So let's convert this back to geometry. Although I think this is already polygon, so we don't need the convert. I'm gonna create a time shift. I'll explain why once in 1 minute. I'm gonna also keep the first frame, and then I'm gonna create the extract transform. So this node is gonna give you a few options, and one of those options is the one that we need. That's gonna be what we're going to use for the transformation, and we want the translation, rotation, and uniform scale. And we want that output as a transform matrix 4x4. So it's a matrix that contains both, actually everything, the rotation, the scale, and the translation. And that's what we are going to be using. Now, the way this computes this matrix, or what you will do usually in Vex, is that you will calculate a matrix for the static geometry and calculate a matrix for the animated geometry, and then compute a difference matrix between those two. But you don't need to do that. This node is gonna do it for you. And then if you have a look here at point as a point attribute, now you have this transform 4x4, which contains that difference matrix. So what I'm gonna do now is create a labs file cache. I'm gonna call this Spaceship TM for transform. And we are going to store this. And before hitting save to disk, I want to make sure that this is time dependent because we want to cache all the frames. And I wanna click this shelf tool, because remember, I want to change those parameters, and then I'm going to save to disk, and I'll see you in a minute. So it is down. Let's hide the position and keep only the transform. And now you can see the transformation, it's changing, and this is the transform we're going to use from now on. I'm not going to show you right now in this video, but I'll show you later. So for now, let's create a null, and let's call this global spaceship transform, and this is our matrix. So in the next video, what we're going to do is create some attributes to separate parts of the spaceship into components that we can actually use to create fractures, to create constraints, etc. So I'll see you in the next one. Okay, so now we are going to create the attribute that is going to help us separate pieces. And for that, I'm going to create a primitive wrangle. And I'm going to call the wrangle extract tags. And those tags are the attribute or the values that are going to allow you to separate different pieces of the spaceship into groups. And for that, one very useful attribute is the path attribute. So if you select the wrangle and then you go to the primitives, you will see that there's an attribute called path. If you don't see it, just make sure that you have it selected on the list. And you can see that it's a bunch of strings separated by slashes. And what this attribute is doing, it's actually describing the hierarchy of the geometry in Maya. So if you were to open this Alembic in Maya and have a look at the outliner, what you will see it's a bunch of groups and objects put into those groups. And this string is basically describing that sort of grouping. So because the hierarchy is stored in the attribute path, we can use it to see if some pieces are grouped together or not, or should be grouped together or not. So what I'm gonna do is use that attribute path to create an attribute called main part. So let's create the attribute. It's gonna be called main part, and I want to use the attribute path for that. So if I set main part equal to path, of course what you're gonna see is that the main part, it's exactly the same as path, but what I want to do is extract some parts of the whole string, and for that I'm gonna use a function called split. So a split is gonna let you separate or split a string by using a part of the string. So in this case I'm gonna use the slash. So let's do comma, and in here I'm basically declaring or saying that slash is gonna be used to separate our attribute path in different chunks. And then from those chunks I want to select only one of them. In this case I know I want the component number 3. So now you can see that we have bottom geo. If I display the path again, you can see that bottom geo, it's the part number 3, as we are saying here, Because if you have a look at the whole string, you will see that this is 0, 1, and 2, and then finally 3. And this is the part that we are extracting. So if I create a color, just for quickly visualizing the attribute main part, random from attribute, set it to primitive, you can see that we have different groups. If you do the exercise of trying to select different parts of the string, you will see that you will get different results. So if I do 4, you can see that now we have a different set of groups of objects, and this might make more sense for you depending on how you are setting the constraints and the RBDs. In my case, I used the part number 3, but you can use different parts of the string to build different groups. In this case, the attribute path is not extremely useful, because usually what you will see is that in a real production, the attribute path not only contains the name of the object, but also there's some information about the material, because lighting usually use the attribute or the path to know which materials they need to assign to each object. In this case, we don't have that. So I'm just gonna use the part 3 of the path. Okay, so now we have our main part. The next thing I want to do is select the part of the geometry that it's going to drive the simulation. As I said before, we want to keep, or we want to use the animation of the spaceship to drive the dynamics. And in order to do that, in this case, what I'm gonna do is I'm gonna select one part of the spaceship that is going to always follow the animation, and it's never going to be dynamic. It's up to you to choose which part. You could choose, for example, the part in the bottom, but it's always going to be kind of hidden. But in this case, I'm gonna use this little part on the top. So I'm gonna create another wrangle, and I'm gonna call it set geo driver. And what I'm gonna do in this wrangle is select which geometry I want to use as the guide, which, as I said before, is gonna be this one here. So I'm gonna click the arrow, then press 9, and select these two elements, and then hit enter. So now you can see that we are selecting by path. And then what I want to do is update the main part attribute. So rather than using the procedural one we created here, I'm gonna explicitly say that the main part is going to be called driver. So let's override the main part attribute by using driver. So now let's have a look at the color again, and you can see that the elements that we selected now have a different color. I'm gonna keep this color here on the side. And now what I'm gonna do is I'm gonna create a split. And the next thing I want to do is separate everything that it's going to deform, which is made of metal, which is pretty much the whole spaceship except the glass. So what I'm gonna do is I'll select again by path, and I'm gonna click on the glass, hit enter, and now you can see that the whole glass is selected, but I'm sure that there's part of the string which is glass, right? You can see it here. And because maybe all the windows in your model in the future in a different project are not going to be contained within the same path, what I will do is I will filter by everything that contains the word glass by using this technique with asterisks. So it's gonna look for the word glass, and everything, it doesn't matter what it is, that it's before the word glass, and then the same after. So as long as the word glass it's on the path, it's gonna match and it's gonna filter correctly. So now I want to invert the selection, and I'm gonna create two nulls. The first one, it's going to be called metal, and the second one, it's going to be called glass. So I think that's it for this video. In the next one, we're gonna keep setting up the metal geometry. So I'll see you on that one. Bye. Now we have everything that we need to start prepping the geometry. So we know that this geometry is going to deform because it's made of metal. But one problem we have is the topology of the spaceship. You can see that there's not like a consistent size on the polygons, which means that it's going to be very difficult to deform it in a way that it actually works. And usually what you will do is you ask the modeler to help you out with the topology, but in this case we can't because I don't have a modeler. So what I'm going to do, it's something that is not very clean, but hopefully it's going to help us, which is basically divide this geometry. So in that way we will get many more points. But we also need to be careful because some elements on this geometry are very small. Like I don't want to deform everything. Like for example, pieces like this one, I want them to be rigid. So what I'm going to do is separate pieces that are big from pieces that are small, and then I only will subdivide the big pieces. So let's start doing that now. I'm gonna create a subnetwork and change its name to filter small. Dive inside, and what I want to do is measure the area of the geometry. So I'm gonna create a null. Let's call the null in geo. And the first thing I'm gonna do is I'll create a measure sub. And the thing is that I want to measure the area of all the connected pieces. And in order to do that, I'm gonna use a connectivity sub. And I'm gonna create a connectivity attribute based on primitive that I'm gonna delete later. And I just want to make sure that I'm not overwriting or creating any sort of conflict with any attribute created by the user before. So what I'm gonna do is I'm gonna call this underscore class, and then in the measure I'm gonna use per piece, and you can see that it's using a piece attribute class. So I'm gonna right click, copy parameter, and paste the same value on the piece attribute with relative reference. So now we have a bunch of different areas that we can use. I also want to give another option to the user where they are not calculating the area based on the face of the polygons of the geometry, but based on the bounding box of the geometry. So what I'm going to do now is I'll create a for loop or a for each loop, and then I'm gonna do the same. I'll right click, copy parameter, and I'm gonna use the same value as the piece attribute. So you can see that now we are iterating on all the connected pieces. So what I'm gonna do now is I'll create a bounding box that's gonna cover the whole geometry. And I'm gonna set the bound to oriented bounding box, so it's a little bit better aligned with the original geometry. The next thing I'm gonna do is I'll measure the area of the whole bounding box. And I'm gonna set the accumulate to throughout. So it's gonna give us the whole area or the addition of the area of each one of the polygons. So you can see all of them have the same value. And what I want to do is copy the resulting area from the bounding box to the original geometry, which is the result of this connectivity. So I'm gonna remove the single pass. You can see that we have a bounding box for every single set of connected pieces. I'm gonna create an attribute copy. And what I want to copy is the area. So connect the nodes, and then I'm gonna change the attribute name from CD to area. But in this case, I want to make sure that the attribute is copied correctly. So I'm gonna use an attribute to match. I know I have this connectivity attribute that we created before, so I'm gonna again right click, copy parameter, activate the match piece, and paste the attribute or the parameter into the attribute to match. And I'm gonna remove the allow p attribute. And now we should have an area that it's pasted correctly, or so I would like to think, but I don't think that's correct, because right now the output of the for each doesn't have temp connectivity attribute that we created before. So I need to make sure that right before the output of the for loop, we are copying the connectivity attribute. So I'm gonna create another attribute copy. I'm gonna remove the allow p attribute, and I'm gonna copy the same attribute that we are using into the second attribute copy by pasting relative reference. Let's see what it's complaining. It's saying that there's an attribute mismatch, so I'm gonna change the group type to primitives, so now we don't have that warning. And this one it's saying the same. I'll do the same here. So now the area should be pasted correctly. So we have areas that goes between 0 to 129. These polygons that have area of 0 are gonna create some problems, so we're gonna solve that in a moment. But for now, what I want to do is I'll delete the connectivity attribute that we created before by using an attribute delete, because the only reason we are creating this attribute is so the measure it's done correctly. So I'll create an attribute delete, and then I'm gonna copy this parameter again. If I'm making some mistakes, we're gonna realize those mistakes once we start running the shots, but it's very difficult to explain while you are doing a setup. So If you realize I'm making a mistake, I'm really sorry, but we're gonna fix it later. So now that I have two options to measure the area, one through the actual geometry and another one through bounding boxes, I want to create a switch so the user can select which approach they want to use. The next thing I want to do is blast any polygon that has an area of 0. So I'm gonna create a blast, and I'm gonna blast any primitive that has an area of 0. And if I do delete non-selected, you can see that we are getting rid of this weird geometry. Another way that we could use to clean the geometry will be through a cleans up, but in this case I'm just gonna stick to the blast. And you can see that also the polygon count, it's changing. Okay, so I'm gonna call this one cleanup. And now we have area on the primitives that we can use to filter things by size. So I'm gonna create a switch, actually not a switch, sorry, a split. And then I'm gonna use an expression to filter by area. A parameter, by doing edit parameter interface, I'm gonna create a float. I'll call it area threshold. It's going to be a float. I'm gonna copy this parameter, paste that parameter into the group, and then I wanna say that any area which is smaller than that, it's going to be put into one of the outputs. So you can see we have this sort of behavior where very tiny pieces are kept on the left and very big pieces are kept on the right. So because I want to filter the small pieces, I want to invert the selection, and I'm gonna create two groups. One on the left, which is going to be big, and another one on the right, which is going to be small. And let's create two outputs. So now we have output 0, output 1. And the other thing I want to do is create another option for the user, so they don't necessarily need to use the actual value for the area, but because sometimes they might want to use a ratio that goes from 0 to 1. So I want to create that option too. And in order to do that, I'm going to create another new attribute, which is gonna be the maximum area, and that maximum area is going to be used to normalize whatever the value of the area that we have on the primitives. So I'm gonna create an attribute promote, and the original name it's area, and I want to promote from primitive to detail. And we don't want to delete the original attribute, I want to keep it, but I want to change the name so it creates a new attribute detail that is going to be called max area. So this is the maximum area we have. And the other attribute we also need to send to detail, it's the minimum area that we have. I'm gonna duplicate the attribute promote. I need to make sure that this one is set to maximum and this one is set to minimum. And I also need to update the name. So we have max area and min area. There you go. And what I need to do is normalize the area by using those new detail attributes. So I'm gonna create a primitive wrangle. And what I want to do first is bring the minimum value that we have on the detail, which seems to be wrong for some reason. Oh yeah, I need to set this to minimum. So minimum is whatever this value is, and maximum is whatever this value is. So I want to bring the minimum, and I'm gonna store it on a variable called min by using the detail function that's going to look for a minimum area attribute on my current geometry, which is a detail attribute. Okay, let's make sure this is correct. So min area seems correct. And the other one that I want to bring is the maximum area. So I'll do the same, and I'm gonna store that maximum area on another variable. And what I want to do now is use these two values to normalize my area. So I'll do a fit or a fit remap or a fit range between my current values of area on the primitives and the maximum and minimum. So let's do f area, it's equal to a fit between the attribute area from the minimum value to its maximum value, and I'm gonna just remap it to 0 to 1. And I'm gonna call this wrangle normalized area. And just for now, I'm gonna put a color just to visualize that new area. And you can see that the biggest areas are set to white, while the very tiny pieces are set to black. So this is working. And I'm gonna create a switch. And this switch is gonna be the one that is gonna let the user to either normalize the area or use the area as it is. So what I'm gonna do now is I'm gonna convert this subnetwork into an HDA. But actually, before doing that, I'm gonna create the interface. So let's go to edit parameter interface. I'm gonna hide all these inputs by setting them to invisible. And the first thing I want to do, or I want to set, is allow the user to set the area from a bounding box or not. So I'm gonna drag this switch as the first input, as the first parameter, and I'm gonna call it to area from bounding box. And it's gonna be a toggle. Press apply. The next thing I want to let the user do is normalize the area. So I'm gonna drag and drop. Let's rename it to normalize area. And this is going to be a toggle again. Press apply. The most important parameter is, of course, the area threshold. So I'm gonna set this to a default, which is going to be 0.1, and I'm gonna drag and drop, and I'm gonna call it filter small, and this is going to be a float. And I want to create a separator between the parameters so they are not jammed together. Press apply, back up. And something else I want to do is put everything inside a folder so it doesn't look disorganized. So I'm gonna create a folder. It's gonna be set to simple, and I'm gonna call it filtering. And let's put everything inside that folder. Let's apply. So now we have something a bit more good looking, and press accept. So what we need to do now is convert this into an OTL by clicking right click, digital asset, create new. And then let's make sure that the type name is going to be the same as the label. And I want to make sure that the menu entry is set to RB. We don't need any branch. The author is going to be RB, and we don't want to prefix type category. We can keep the library path as the default. Press accept or create. So this is our filter small OTL. I'm gonna hit accept. One thing I want to do now is rename the output. So I'll right click, type properties, and let's go to the input output tab. And the first output is going to be big geo, and the other one is going to be small geo. And press accept. So now if you hover your mouse over the output, it's going to display the name big geo and small geo. Press save now type, match current definition, and now we have our OTL ready. So what I'm gonna do now is create two nulls. The first null is going to be the big geometry, and the other one is going to be the small one. And just for visualization, although I'm gonna delete it later, but just for now I'm gonna create two colors. The big geometry is going to be green, and the other one, the small one, is going to be red. So if we merge them together, you can see the small pieces that we are keeping. And I'm gonna play a little bit with the parameters. I want to use the area from bounding box, and I want to also normalize the area. And I'm gonna use a very tiny value, 0.05. Okay, let's remove the merge. And now we are ready to continue with the subdivision of the pieces. So I'm gonna create a for each name primitive. I'm gonna plug this here, and rather than name, I'll use the attribute path. So now we are iterating on path. I'm gonna click single path, find a geometry, any geometry, like this one for example, and then I'm gonna do the process on this one, see how it looks, and then we can remove the single path. For the subdivision, I'm gonna use a divide sub. And then this divide sub, it's gonna create some new polygons that are gonna help us deforming this geometry. So in the divide, let's make sure that we set breaker polygon on. And as you can see, it's adding some new polygons. This is not the smartest way to do this, but it's going to work. At least it's going to give us more points to deform. And then what we need to do is just find some values that are going to help us out. So I'm gonna change this to 0.2, 0.2, 0.2, and as you can see, we already have more polygons to work. And I'm gonna leave it like that. I'm gonna create another divide just to remove any sort of n-gon we have just by triangulating everything. And then finally I'm gonna put this into a compile sub, or a compile block, sorry. Make sure this is set to multi-thread when compiled, and take the single pass. So now we have the whole spaceship subdivided with enough points to deform. We can proceed to create a merge. Merge these two geometries together. We don't need these colors anymore. This was just for visualization purposes. And we're going to cache. So let's create a labs file cache. Let's look for the Rebelway shelf. Select the file cache, click the fix labs cache. That's gonna change the parameters, and let's update the name. I'm gonna call this render geo because this is the geometry that we're going to be not only deforming but also rendering. I want to cache only one frame, so I'm gonna untick the time dependent cache and I'll click save to disk. I want to also create a group that is going to help us out in the future to separate things. This group is gonna be called render geo. It's gonna be a primitive group, and I want to create a null so we can easily select this geometry later from other parts of the setup. And I'm gonna call this geo target for the formation. So in the next video, what we're going to do is start fracturing the geometry so we can use it for our RBD dynamics. So I'll see you on the next video. Okay, so now that we have that part of the setup done and we have the render geometry ready for the formation, let's make some room here. The next step is to create the geometry for the RBD dynamic. For that, what we will do is give some thickness to this geometry, because as you can see, it's a bunch of flat polygons. It's all the geometry, it's basically open. We need geometry with some thickness for the RBD. So let's do that now. I'm gonna do a for each loop that it's going to use this attribute that we created earlier, the main part attribute. And I'm gonna iterate on each main part, and I'm gonna add some thickness to this geometry. So let's do that. Let's create a for each, name primitive, and let's change the name to main part. That should iterate on each one of those main parts. And now let's think a little bit. How can we give some thickness to this geometry? One way could be to create a polygon extrusion. Give it some distance, maybe changing the extrusion mode to point normal, and then giving an output back, activate the output back so we have some actual thickness. And this might work. This might be good enough actually, and you could fracture this geometry. But I'm not gonna use this technique. What I'm gonna use are VDVs instead. So let's delete that and let's create a VDV from polygons. And what's going to happen is, because the geometry is open, this VDV from polygons won't work straight away. But we can use it to create an unsigned distance field by activating this parameter. And it's a bit difficult to see right now, so I'm going to change the background to black. And as you can see, or I hope you can see, there's a very thin black line. When you take this parameter on, what's going to happen is that each one of the voxels, it's going to store the distance to the surface, where darker values are closer to 0, and the whiter it gets, or the brighter it gets, the further away we are from the polygons. So if you imagine this is the surface, the further we go away from that surface, we start having bigger and bigger values. So say, for example, on the surface or on the polygon, that distance is 0, then it goes to 1, then 2 and 3 and so on. So what we want to do is use these values to create a new surface, and for that we need to use a convert VDV, because this is right now density or fog. What we need to do is convert this back into an actual SDF. So let's do VDV and change this to fog to SDF. And what's happening now is that we need to modify the fog ISO value. So the way an SDF works is that, say for example you have a sphere, this is the worst sphere ever, but imagine this is a sphere, and then we create a VDV out of this sphere. What's going to happen is that whatever is inside the sphere, it's negative. So we're going to get -1, -2, -3, and so on. And when the further away it gets from the surface, and by surface I mean the border of the sphere, those values become positive, right? So 2, 3, 4, and so on. And whenever the value is 0, the VDV representation is going to display a solid surface. But if you imagine this is some sort of gradient of values, you could very easily offset that value of 0, saying that, for example, now I want 1 to be the new 0, and what's going to happen is that the sphere is going to grow. Or maybe you want the value of 3 to be the new 0, and what's going to happen is that surface representation is going to be in a new position now. You do that by basically remapping where that 0 value is now. And you can do that with this fog ISO value. So if I bring that to 0, and then I slowly start increasing what you can see is that we are saying that whatever it's at this distance from the original polygon, it's gonna become the new 0. And if you go away of the, like if you go too far, then what's gonna happen is that because this is a VDV, there's not any more information, because there is this parameter called exterior band voxels, which limits the amount of the voxels that you can use away from the surface of the polygon. In order to create some thickness that you can use in RVDs, this is more than enough. So I'm gonna just make this a little bit thicker, and then what you can do to make this thicker if you want is create a VDV reshape, and then you have more control on what kind of thickness you want. I'm gonna set this to 0 for now, so the default it's going to be 0. And then after this is done, we can convert this into a geometry by using a VDV convert back to polygons. So now we have a geometry that is thick and that you can fracture and use in RVDs. But the problem is that now we have this new name, all the attributes that we had before are lost. So we need to make sure that we keep at least the attribute that we are using to iterate on in case we want to use it later. So I'm gonna do an attribute copy. And then in here I'm gonna transfer or copy main part. And let's set this to primitives, because we know main part was a primitive attribute. And now we have main part, and I don't want to have name, because name is created by these fields. So if you middle click here, you can see that there's a name, which is called surface, because that's the name of the field. But we don't need that name, so I'm gonna do an attribute delete the name. So now we should have only what we need. And lastly, what I'm going to do is put all this stuff into a compile block, so everything is evaluated as a single node, and it can be run parallelized on the computer. So let's activate the multi-thread when compiled. Let's deactivate the single pass, and what we should see once this is finished is that now we have thick geometry, which it's effectively thicker than what we had before, but because we are going to have so many layers of effects on top of this thing, smoke, RVD debris, there's gonna be some trees, we won't notice that change in the thickness, which means that this is gonna work well enough. The next thing I want to do is place all this into a subnetwork, so let's do that now. And let's create an explode view, just to have a look at the different elements. And as you can see, this is every single main part separated. If you change this parameter to main part, you will see that these are all the different main parts, and that each one of them have thickness. The next step is to convert this into an HDA or OTL, just like we did with this one, just because I'm planning to use this in other parts of the setup, and I don't want to be copying a subnetwork, because mostly when you want to reuse setup like this in other parts of a file, or maybe you want to give this to someone else, if I make some modifications to this to make it better, I want like every other instance of this subnet in my file to be updated with that latest modification. And the easiest way to do that is by using HDAs. So that's one of the reasons I'm trying to encapsulate this into actual HDA rather than keeping it as a subnetwork. And that's something we will do in the next video, so I'll see you there. Alright, so select the subnetwork, dive inside. I'm gonna start by creating one null that I'm gonna call ingeo. And then let's go back up. Let's rename the subnetwork to thickness from geo, which is going to be the name of the OTL. And I'm just gonna edit the parameter interface. Let's hide all these inputs. And then I just need to think about what parameters I need to expose to the user. And the most important thing, I feel, it's the attribute that we are using to iterate, which in this case, it's main part, but you as a user might decide that you want to use a different attribute. So I'm gonna drag and drop the attribute name, and I'm gonna update the name to piece attribute. Once you have that done, I'm gonna click accept, and what I want to make sure is that the for loop only runs if there's something in the piece attribute, because if you don't put anything here and you run the for loop, what's gonna happen is that it's gonna try to create one volume for each one of the polygons. If you set the for loop or the for each to run on an attribute and you don't give it anything, what's gonna do is it's just gonna run on each one of the primitives, and you really don't want to do that. That's probably gonna crash Houdini. So what I'm gonna do is I'm gonna create a switch, and I just want to run the for loop if there is something inside the piece attribute value. So what I want to do is copy this parameter, then select the switch, and I'm gonna use a function called strlen. So I'm gonna first paste that parameter here. I wanna evaluate that value as a string. And then what I need to do is say that if strlen of that string, which is the attribute that we just copied, it's not bigger than 0, then we're gonna basically use the output of the InGeo. But if the string is bigger than 0, it means that we are actually trying to use an attribute. Then in that case, it's going to use the for each. So if that value is bigger than 0, then do something. If not, then do nothing. And I just realized that I'm doing something stupid. We don't really need the if condition, so I'm gonna remove the if from there. Okay, so now if the length of the string that's coming on the piece attribute is bigger than 0, then the resulting value is gonna be 1. But if we delete any value from here, so it's basically an empty string, then it's not going to do anything. And actually what I should output is just a null, so they know that there's something dodgy going on, and I'm just gonna call this null empty. So now we are going to carry on editing the parameter interface. Just for now, let me bring back the main part. And something else that I want to do is make sure that that main part is not the default parameter, because we want the default to be empty. So press apply, and then if I write something in there, you're going to see that now that value is bold, while before the string wasn't bold, which meant that that was the default value. All right, so I'm gonna create a separator and a spacer, and press apply, and let's carry on bringing the other parameters. The next one, it's the voxel size on the PDV from polygons. But in order to make this look a little bit better, what I'm gonna do is I'm just gonna create one folder. I'm gonna make it simple, and the name is gonna be volume properties. And inside that folder, I'm just gonna drag the voxel size, and then let's see what else we need. We definitely need the fog ISO value from the convert PDV, and I want to change the default because that value is kind of weird, so I'm gonna make it 0.1. The voxel size, it's also going to be 0.1, and then we also need the offset from the reshape, so I'm gonna drag and drop the offset. And when we are converting the PDV into a geometry, I want to also have control on the adaptivity, so we don't create some crazy heavy geometry by default. And the default value I think will be 0.5. So if we want to make that geometry more detailed, I just need to decrease the value on the OTL itself. So press apply, save your scene, and then you can see that the parameters are promoted to the user. And the last thing I want to do is basically copy the piece attribute into the attribute copy. So once you create the VDVs and the geometry is created, we copy back the main part into the new geometry. And if you are using any other attribute to iterate, well, you're gonna copy that attribute. So I think we are ready to create that OTL. So I'm gonna hit accept. Let's have a look. Perfect. So I'm gonna right click on the subnetwork, digital asset, create new. I'm gonna change the menu entry to RB. Thickness from geo, it's correct. The asset label, it's correct. It's thickness from geo. We don't want any branch. Version, it's correct. Now prefix type category, so everything here seems correct. I'm just gonna click create. If at some point you decide that you want to change the menu entry, so it doesn't go into the RB menu entry, all you need to do is go into the interactive tab, and then you go into the shelf tools tab, and finally you go into the context tab. And because when we created the OTL, we decided that the OTL was gonna be put into the RB menu entry, then that's the value that was used here. But if you want to put it somewhere else, all you need to do is just change this value. So I'm gonna click accept. I'm gonna match the current definition. And then what I'm gonna do in the next video is I'm just gonna cache this geometry, and we are also going to fracture the glass. So I'll see you in that one. Now let's proceed to save this geometry. Create a labs file cache. Let's name it thickness geo. Don't forget to open your Rebelway shelf. And with the labs file cache selected, click the fix labs cache. This is only one frame, we don't need to cache different frames, so let's untick the time dependent cache and click save to disk. Now we have the geometry we need, and we have the geometry for rendering. So we created a group called render geo on this one. I'm gonna create another group which is going to be the dynamic geometry on this one. I'm gonna create a null here just in case I want to access the geometry directly. And let's merge these two together. So now we have the geometry for rendering and the geometry for dynamics together. Let's create an output. So now we are almost done with the ship preparation. The only thing left is fracturing the glass. So let's start doing that. Okay, so let's now fracture the glass. Select the glass null and have a look at the geometry, which is kind of a mess. There are some vertices that are not properly separated. There is one vertex here which is kind of floating. So because I don't have a modeler to ask, I'm just gonna try to fix this so it works well enough for our purposes in effects. So I'm gonna add a fuse shop that should fix the problem with this vertex. So now it's 1. The next thing I'm gonna do is do the poly extrusion because we need some thickness. Now, the reason I'm not using this tool to create the thickness, it's because this is geometry that I actually want to render. While this geometry here, it's only for simulation. While this one here, it's the one that we are going to be rendering. In this case, we need to use a poly extrude. Let's add some negative distance, so we push backwards. I always do it by point normal. We need to also output back geometry, so it have some proper thickness. The problem is that this is going to basically reverse the normals. Now the normals are looking in the wrong direction, and we need to invert them. So in order to do that, I'm going to reverse the order of the vertices, and then I'm going to add a normal, so it recomputes the normal. The next thing I'm going to do is add more resolution in the same way we did to the geometry by adding a divide sub. Let's activate breaker polygons and set it to 0.1, 0.1, 0.1. And now we need to fix the end guns, so I'm going to add another divide, which is going to triangulate those polygons. And now we have geometry that it's kind of ready to work. The only thing I don't like is this vertex here, but we're going to carry on with it as it is. In order to fracture this, you might be aware that there is this node called RBD fracture material or RBD material fracture, which has an option here to create anything that you want, but I'm not going to use it because I find it very slow. It works great when you're gonna fracture a wall or a piece of geometry which is very simple, or if you are just testing on boxes or things like that, it works great. But once you start working with real production geometry, which tends to be very heavy, this is no longer an option to me, at least. Like, I've never used it before just because it's so slow. So what I'm going to do is add some noise to geometry, fracture, and then remove the noise back. So let's add a point VOP. Let's add some turbulent noise. And this noise needs to be 3D because we are going to add it to the position. So let's create an add to the current position, this noise, and the output needs to be positioned. So now you can see we have some noise applied to the geometry, and I'm going to change that noise type to original Perlin noise, and I'm going to reduce the amplitude to something smaller, and the frequency is going to be higher. So we have more detail on the noise. Now what I'm going to do is scatter some points on the geometry. I'm going to remove the relaxed iterations so it's a little bit more organic, and then I'm going to add a Voronoi fracture. Now let's visualize by name. And as you can see, the fractures are straight, which makes sense because that's how Voronoi fracture works. So the next thing we need to do is to remove that noise from the geometry. So in order to do that, we needed to store an attribute before the noise, which is the original position. So let's do that. Let's create a rest. And this is going to store the position as an attribute called rest, which is another vector that it's exactly the same as position. The only thing we need to make sure is that this rest is calculated only once. So if the geometry is animated, you need to make sure that rest vector is calculated on the geometry in a single frame. Otherwise the rest is not going to be useful at all. And then what I'm going to do after the Voronoi fracture, it's create a point wrangle and say that the new position, it's going to be equal to rest. And that's going to bring everything back, and now we have this sort of noisy kind of fracture. But I would like to have a less strong noise, so I'm going to reduce the value of the amplitude. Probably the pieces are too big, so I'm going to increase the amount of points. And I'm gonna set it to 1000. It's gonna be a bit slow, but it's gonna give us pieces that are smaller, but I don't wanna go too small because I know that we are never going to get too close to the spaceship. Most of this is going to be covered by smoke and particles, debris, so I'm just gonna go with this size. But if you like, you can go even smaller than this. And I wouldn't worry too much about creating clusters or anything like that, just because later in future videos, we are going to learn how to do clustering with constraints. So for now, I'm just gonna keep this like it is. Let's rename this wrangle to P from rest. And I think we are ready to cache. So the only thing left is that we need to check the attributes, make sure that we have everything that we need. And I'm gonna double check that main part, it's still working. So let's go to the primitives, have a look at the main part, and make sure that it's not missing anywhere. It looks like it's correct, still windows. Sometimes when you create new geometry with something like a poly extrude, some of the new polygons are not going to inherit all the attributes, so you need to make sure that we still have them there. And the other thing I don't like is the naming of the Voronoi it's creating, so let's fix that. I'm gonna call this glass. Now you have glass and the number of the P's. I'm gonna add an underscore, and that's it. I'm gonna keep it like that. Cool. So now let's create a labs file cache, change its name to glass fracture, make sure that it's not time dependent, fix, and then cache. Let's create a null, and this is going to be out glass fracture. And this is it for the glass. For now, just keep in mind that if you want, you might add more points to the scatter, so you get smaller pieces. But I'm gonna go with this value just to be able to iterate quickly. And this is pretty much it for the spaceship preparation. What we are going to start doing in the next videos, it's prepare the dynamics setup. That's gonna get quite involved, so be a bit patient with it. It's gonna be a lot of information, but I hope it's gonna be fun. So I'll see you in the next one. Before we go ahead with the DOP network, what I want to show you, it's a way to streamline the caching of all these caches. Just because imagine you are starting on a new shot and you have to cache every single thing in the scene. That means that you will have to go one by one, pressing save to disk, pressing save to disk again until you cache them all. And that can get really tedious. So what we tend to do, it's something called a ROP dependency network, which is done in either in the out context or in a ROP network. And this is done by using a node called fetch or any other proprietary node that people use at their companies. And what this does is that this is going to bring or fetch the ROP geometry node that exists within each one of these file caches. So if you dive inside this file cache or the labs file cache, you will see that there is a ROP geometry output, and this is the one that it's actually doing the caching. So what we want to do is fetch this ROP geometry output into the out context and then run this cache from there. That way what we can do is basically create a lot of fetches that are fetching the ROP geometry from each one of these nodes, and then daisy chain them in a way that you can run them in sequence. Currently, there is two ways to do that. One, it's using the approach that I just mentioned, using out context, and the other approach is using PDG. So I'm gonna show you a little bit of both. I'm not an expert with PDG by any means. I haven't used it that much, so I'm just gonna tell you the basics or what I have used so far. But keep in mind that what I'm gonna explain you, it's just the fundamentals or the basics or basically what I have learned. So when you go to each one of these labs caches, you will see that they have this tiny hat here as a button. That button is not present if you create a file cache. So that's why we are using this one instead. If you click this button, what's going to happen is that it's going to create a top network at the object level. If you go here to the advanced tab and then you go to node generation, you will see that here's the path where this is going to create the top network, which by default is the object level, which to me it's fine. So what I'm going to do is, for each one of these file caches, I'm going to create one node in the top network, and then we are going to run them all. So in order to show you that that's working, I basically deleted all the geometries that we had cached before, so you can see that we have no points. I did that by clicking this little thing here, which is going to let you clean the geometry that you have cached. So I just want to show you that everything is empty, because then I'll show you that we have the geometry back again once we cache them all using the top network. So I'm gonna come to the environment prep. This is the only one I'm not gonna delete just because it's slow to cache. So select this environment split and then click this button. What's gonna happen is that if you go outside to the object level and then go have a look, you will see this top network. Let's place it somewhere here under the top and then dive inside by double clicking. And you can see that this created this node called environment split. What we're going to do next, do the same for the other labs file caches. So let's go back up. We now have the environment prep already done. So now let's go inside the spaceship prep. The next one we want to cache is the spaceship transform. So let's click here. I'm gonna open a new floating panel, dive inside the topnet, and now you can see the spaceship TM, it's been created inside. So let's connect this to the environment split. Let's do the same for the render geometry. Click the hat, it creates this render geometry. Let's plug it here. I'm not connecting this in sequences like this, for example, like this one to this one, just because I know that this render geometry doesn't need this transform to be cached. They can be all run in parallel. So what I'm gonna do is place them one next to the other so they can be run in parallel by the computer. Let's do the same with the thickness geo. And let's do the same with the glass fracture. Let's do merge. I'm gonna merge this all. And something I just realized is that actually we don't need to cache this before this one. So I'm gonna also make the environment run in parallel. So let's put this one also next to the others. And what we need to do in order to run these caches is select the last merge and then do generate node. That's gonna generate the work items for every single one of these nodes. You can see that the spaceship transform has more work items. That's because this is frame sequences, while these others only have one frame because they are only one static geometry. Now let's go ahead and right click again on the merge, cook node. So what's going to happen is that it's going to start working on each one of them. You can see that the environment split is already done because it was already cached. You can see that the spaceship transform is being cached frame by frame. You can see that the render geometry is already done. Thickness geo is already done. And the glass fracture is still working, which means that this branch of the network is still cooking. And we need to wait until the spaceship transform is done. So now every single one of these labs caches should have geometry. You can see it's back in there. It's back in there, which means that you don't have to go one by one in order to cache nodes. All you need to do is go to the top network, generate node, and then cook nodes, and that's gonna cache them all. But this gets a little bit more involved, and we're gonna see that in the future because generating the dependencies is not as straightforward. The last thing I'm gonna do here is do a wait for all. So once we start working in the other parts of the setup, when we create new fetches here, every single node that it's after this wait for all, it's gonna wait for this to be finished before they start running their whatever they are running. So this is the approach for PDG. What I want to show you now, it's a more kind of classical approach, which it's been used for years. It's what I've seen used in most of the companies, which is a ROP dependency network. So I'm gonna again delete everything by clicking this little button, press yes, and now you can see that this is empty. I'm gonna do it for every single one of these caches and I'll be back. So it's done. Now you can see that this geometry is empty. It's the same for all of them. Actually, I need to click reload here. Now it's empty. So what I'm gonna do now is do something similar to what we did with the top network, but I'm gonna do it as a ROP dependency. So let's go to the out context and let's create a fetch. From this fetch, what we're going to do, it's call the file cache that we want to cache in the out context. So to make that easier, what I'm gonna do is go back to the object level. I'm gonna create a new floating panel, and then in here I'm gonna go to the out context, and then I'm gonna do something similar to what we did before. I'm gonna cache first the environment prep. I'm gonna set this to manual, so it's not cooking the heavy environment all the time. And if you dive inside the labs file cache by double clicking on it, you will see, as I said before, this ROP geometry output, and this is what we want to connect to this fetch. I'm gonna click and drag, And now this fetch is pointing to this render geometry. So if you click render on the fetch, what's going to happen is that this fetch is going to render whatever this drop geometry node is caching. So let's carry on and do the same with the other node. So let's go outside. Let's create another fetch on the out context, connect it. Let's name this one fetch environment, and this one it's going to be, for example, fetch spaceship TM. So let's go to spaceship prep. Let's dive inside this node and click and drag the render geometry here again. So now this one is pointing to the environment, this one is pointing to a spaceship. And then if I wanted to catch them all I need to do is create a batch. And then if I, with the batch selected, if I click render, what's going to happen is that Houdini it's going to cache this, then it's going to cache this, and then it's going to do everything in order, kind of a sequence. But it can be very tedious to do that same process for every single one. And you can imagine that in a final scene, we are going to have a lot of these nodes. So doing that by hand is going to be a pain. So what I want to do now, it's a little Python script that's going to do that for us. So I'm going to delete. Let's remain with this window open. And then let's create a new tool on the Rebelway shelf. And let's call this one create fetch. Fetch, because it's going to be done only for the labs node. And I want to add an icon to it, which is the same that we used before, edit tool. I'm going to copy this icon and paste this on the icon for the new tool, press apply, and now we need to write the script. So I'll do what we did before. I'm gonna copy the script and then I'll explain what it's doing. So press apply, and now what this is doing, it's similar to what we have done before for the fixing of the file cache. We are storing all the nodes that are selected, and then I'm also creating a variable that contains the full path to the out context. And then if we have nodes selected, and only if this is true, if we have a node selected, we are gonna iterate on all the nodes. We're going to check again if the string labs file cache is present on the node type name, which it is. If you middle click here, you will see that the node type name, it's labs column file cache column 2.0. So this is going to be true if you have one of these nodes selected. And then what I'm going to do is change the color to pink, so that way I know that if this node is pink, it means that I already run that process for that node. Otherwise, it's going to be very difficult to know if I'm missing one of these nodes or not. So I want to change the color when we run the process on it. And then what I'm doing here, it's storing the full path to the ROP node that is inside of the labs cache, which is this one. So you can see that for each one of these nodes that we have selected, which in this case is only this one, we are getting the path to this node and we are adding the path to the render node that it's inside. Then what I'm doing, it's on the out context, which you're gonna see here in 1 minute. I'm going to create one fetch ROP, which you already know what it is. It's the fetch node we created before. And I'm gonna change the name of that fetch node to out plus the name of this node. So any fetch ROP created by this shelf tool, when selecting this node, it's going to be called out thickness geo. And then on that fetch, I'm going to just create one here very quickly. I want to update this parameter with the path to this node, which we already have stored in this variable called ROP geo. So I'm saying that the fetch parm source, which is this parameter here, it's going to be set to the full path to the render geometry inside the labs file cache. So press apply, accept. I'm gonna delete this one. I'm gonna select the thickness geo, or actually I'm gonna go to the first one that we need to cache, which is the environment prep. I'm gonna select the environment split, and then I'm gonna click this shelf tool. You can see it changes the color, and then if I press space G, it's gonna find the only node that we have there, which is this out environment split. You can see the path is pointing to the render inside this environment split. And now the only thing we need to do is go into the spaceship prep and do the same for this other node. So I'm going to select the spaceship transform, click on the shelf tool. I'm going to place it next to the other because, as I mentioned before, all these tasks can be run in parallel. I'm going to do the same for this one. And let's do it for all of them. And these are all the caches that we are doing here. So I'm going to merge them all, and then I'm going to create a batch. Now remember, this is empty. So after we click render here, what's going to happen is that these things are going to be cooked and we should get geometry. So I'm going to click on render, I'm going to pause, and then I'll be back in 1 minute. Okay, this is done, and you might have noticed that it took a long time. And the reason is that even though all these ROPs are set to cache only one frame, because that's the value or the parameter that we set in each one of these labs file cache, it is running all the frames for each one of them, just because the transform spaceship, it's calculated for the whole frame range. So rather than caching only one frame for each one of them and then all the frames for this one, it's caching all the frames for all of them, which means that the boolean that it's being calculated on the environment split. It's being calculated for the whole frame range, and that it's very slow. One way to solve this is use a pre-post graph. And the way this works is that it's going to first cook or calculate anything that goes into the first input, then whatever goes into the middle input, and lastly whatever is connected to the third input. So I'm gonna disconnect the transform, which we know it's frame dependent or time dependent, and let's connect that to the first input, and everything else connects into the second input. And this way this is gonna be cooked first, and then this is gonna be cooked next. I know I don't wanna cook the environment split because it's already cooked, it's very heavy, so I'm gonna bypass it, and then I'm gonna click render. So as you can see now, it's cooking the spaceship transform, which is quite fast. Once this is done, it's going to move on and cook these ones, but only once. This is done now. Let's have a look. I'm gonna for now close this window, and now we have the spaceship, the thickness of the spaceship, we have the render geometry, and we have the glass fracture. So what we did here on the out context is also very useful, but in general it's going to be slower than PDG, especially if you are working on your own computer at home. It will be different if you were working in a render farm or a company which has a render farm, because then each one of these jobs will be sent to a different machine, and then it will make it much faster. So that's it for this video. In the next one we're going to continue doing the spaceship setup, so I'll see you on that one.